Welcome to HexCon 2021. My name is Gus Clark, one of the organizers for this year's event. Firstly, we'd like to thank you, the community, for keeping and maintaining this event a free event, free of advertisement, free of sponsorship, and community-driven, year on year. Secondly, I'd like to thank all of the researchers for the excellent talks that they submitted. Before we begin, there's a few things I'd like to take you through. The first one being is that all the talks are pre-recorded and will be uploaded to YouTube afterwards. Secondly, all discussions will happen on the HackSouth Discord server. If you're not a member, you can currently join by going to hacksouth.africa. Thirdly, the researchers or speakers will be available for comment or discussion or to answer your questions afterwards in the HackSouth Discord server. Now I'd like to hand over to the intro for our first speaker. Thank you.
Hello, welcome to HexCon. My name is Rogan Dawes, and I'm going to be sharing with you what I learned about keylock remote control systems. I am a researcher for Orange Cyber Defense, and we hack, build, train, scan, and do research. So what is this presentation about? This whole adventure started when my neighborhood decided to apply for permission to close the street entrances. We had automated gates at 2 of the entrances and wanted to allow residents to open and close them. This would be done using a remote transmitter, much like many have in their homes. This talk covers a few aspects of this journey: why we chose Keylock, what Keylock actually is and how it works, as well as my experiences obtaining full access to the hardware, both receiver and transmitter, as well as repurposing it for use around my home. While it does focus on a particular manufacturer, I won't be revealing the manufacturer key or too much detail about how I was able to find it, as it would expose a significant number of people to attacks, including myself. So, choosing remotes. We wanted transmitters that could be enabled and disabled individually. Having lived in a townhouse complex previously, I was familiar with the flag days, where the code on the receiver gets changed because one transmitter has been lost or stolen, and everybody has to come to the gate to get their transmitters updated to the new code. These are rather inconvenient for 26 households. I definitely did not want to try that in an even larger group. We also wanted to have something a bit better than the average gate remote, because of smart people like Andrew Mohawk, who demonstrated in 2012 how to snoop and replay fixed code remotes. He managed to decode the bit pattern transmitted and replay arbitrary codes using a cheap transmitter. Not great for a community of 150 households to have to go out and buy a whole new set of remotes when this sort of thing starts getting out. So right off the bat, we wanted something that would be a bit better. Centurion gate motors are pretty much the gold standard for gate motors in South Africa, I think. I'm really not aware of anyone else that has close to the market penetration that Centurion does. We ended up going with the D5 Evo, which was well suited to our requirements. This is quite a smart controller, with time of day settings to open and close the gates, perfect for our access permit conditions. It also has a built-in receiver for remotes, which use the Keylock system. Sounds perfect, right? Looking at the documentation, it turns out that the controller is capable of learning up to 500 Nova rolling code remote control buttons. While this may have been feasible to manage the remotes for 150 households directly on the gate controller, and it would start getting tight if each household had more than 3 remotes, it was not possible to coordinate the configuration between 2 gates at the top and bottom of the street, and that at the time at any rate. And then their Super Helix receiver was not yet available. So this is where we ended up, a receiver that can accommodate up to 8,000 enrolled transmitters split across 2 relays. And then the matter of managing the transmitters arose. Since we had 2 gates, we'd need to enroll the transmitters into both receivers, as well as having backups in case anything happened to the receivers. Fortunately, the vendor provides an app to manage the database, including enrolling transmitters via a USB cable, which was nice. Unfortunately, the app was not exactly designed for mass enrollment, requiring multiple clicks just to enroll a single transmitter on one relay. Then scroll through 4,000 entries to get to this corresponding entry for the second relay, and then back again for the next transmitter. Fortunately, the app was written in .NET, making it relatively easy to decompile and figure out how to speak to the receiver and capture the details of the buttons that were being pressed. So I wrote a Java app, because that's what I know, to interface with the receiver and simply increment the slot for each button, alternating between the two relays, dumping the data into the same SQLite database format used by the vendor app. It would then export the database into a text file, which could be saved onto a micro SD card and taken to each gate to be loaded. And so it worked for several years. So let's talk about Keylock itself. In order for a secure remote control system to be implemented, it's only possible if two conditions are met. A large number of possible combinations must be available, and the system may never respond twice to the same transmitted code. So Keylock was designed with these principles in mind back in the 80s right here in South Africa. It was then purchased by Microchip in the mid-90s and ended up being used in remotes around the world, including many motor car manufacturers. The first requirement is achieved by transmitting a 66-bit code word, resulting in a much larger search space than the 10-bit code word that Andrew was able to brute force. And the second requirement is achieved by including a 16-bit incrementing counter that is synchronized between the transmitter and the receiver. The receiver will only react if the counter is greater than the last one it's seen, or so a simple replay attack is foiled. But hold on, you might be thinking. If it's just a simple incrementing counter, surely the attacker can also increment the counter and play the next one in the sequence. That attack is prevented by encrypting the counter and some other data, using a shared key that is unique to each transmitter, resulting in a 32-bit scrambled block making up part of those previously mentioned 66 bits. So no, it's not truly a 66-bit random space, only 32 bits. The remaining 34 bits have specific meanings and are not random. So the fact that it's reduced from 66 down to 32 bits is less of an issue if you don't have an offline oracle to tell you when you find the right value though, and have to actually do the transmission and observe the receiver's actions. The vendor estimated that it would take in the order of billions of years to iterate through all the possibilities, making it pretty infeasible to attack using brute force. This is analogous to running Hashcat on a leaked password hash, compared to attempting a brute force attack login via the login form of your target. One of the things that they had to consider in their design was desynchronization though. If the transmitter button is pressed outside of the range of the receiver, at some point that counter is going to be larger than the gate's counter. So logic was designed to account for this. Generally what happens is that if the received value is within 16 of the last value seen by the receiver, it will immediately update its stored value and operate its action. If it's more than 16 values away, it will simply store the last value that it's seen temporarily, and then if the very next value that it sees is the next sequence number, it will update the value that is stored for that particular transmitter. And so the synchronization can be restored. Some failure modes of these transmitters? Well, there's two, which is actually slightly different to the more conventional transmitters. In this case, if you can clone, with enough information, you can clone a remote and you can trigger its actions similarly to the legitimate remote. But there's a second failure mode, which is denial of service. If I can convince the receiver to accept a forged transmission, I can increment that counter value beyond the 32K window and prevent the original transmitter from functioning at all. So let's talk a bit about what the transmissions look like over the air. Transmitters use amplitude shift keying and on-off keying to transmit the 66 bits, surrounded by a preamble and a header, and ended by a guard period of no transmission. The transmitters use varying lengths of positives and ones and zeros, or should I say highs and lows, to convey a logic 0 or a logic 1. Those are then combined into a complete transmission, starting with the preamble, the header, the encrypted portion of the transmission being 32 bits, the fixed portion of the transmission being 34 bits, and then the guard time to signal the end of the transmission. Then the breakdown of the encrypted and clear text portions, and note that it is back to front because it's transmitted least significant bit first. The encrypted portion contains the synchronization counter, which is a 16-bit value. It contains 10 bits used for discrimination. That allows you to verify that you've decrypted the correct portion, the correct, that what you have decrypted matches the fixed portion of the transmission. There are 2 bits for overflows, and then there are the 4 bits of the buttons that were being pressed. Then in the fixed portion, you've got the serial number of the transmitter being 28 bits, the buttons repeated, which allows you to verify that the transmission, the fixed portion and the encrypted portion matches up. Then 2 bits for statuses, voltage low and repeat, allow you to determine whether the button has been held down and also whether the battery is about to die. Okay, so the counter is encrypted to prevent it from being tampered with. And this is done using a shared key, symmetric key, known by both the transmitter and the receiver. How is this key shared between the receiver and the transmitter then? Well, the keylock documentation actually leaves the key derivation function up to the implementer, although there is a reference implementation that appears to be used in practice. There are 2 forms of learning or enrollment in classic keylock: normal learn and secure learn. In the normal learn process, the key is derived from a combination of a 64-bit manufacturer key, which must be kept completely secret, and the unique 28-bit serial number of the transmitter, used as input into the manufacturer's chosen key derivation function. The same function is used when programming the transmitter to generate a unique key that is written to the write-only memory in the chip, as is used in the receiver to derive the shared key. In this way, the receiver does not need to know the keys of all possible transmitters in advance, but can derive them when needed. Unfortunately, this does mean that the receiver by necessity must contain a copy of the 64-bit manufacturer key, and therefore needs to implement controls to ensure that this key does not leak, or else the entire ecosystem that shares that manufacturer key and key derivation function would be compromised. The problem with the normal learn process is that one of the inputs into the key derivation function is exposed every time the remote is operated, because the serial number is included in the transmission. An attacker who knows the manufacturer key and the key derivation function can derive the same encryption key and generate forged transmissions. As a result, Keylock included a secure learn process. In this process, the key is derived from a combination of the 64-bit manufacturer key and a 32-bit random seed used as input into the chosen key derivation function. The random seed is only transmitted when a combination of keys or buttons on the transmitter are pressed, and is only used, and this is only done when enrolling a transmitter onto a receiver. In the normal way of things, the seed is never transmitted. In fact, the transmitters can be programmed that after a few operations, that seed may never be transmitted again. This helps to keep the seed protected. So let's talk about the key derivation functions then. The manufacturer knows the key derivation function and the manufacturer key. They use this KDF in the manufacturer key and the transmitter serial number to program the transmitter with a shared key and that serial number. The receiver contains an implementation of the key derivation function as well as the manufacturer key. It receives the transmitter serial number or the seed, and from that it can derive the shared key. So the transmitter then will encrypt its counter using that shared key, and the receiver can then decrypt that as well. So this is the manufacturer's suggested key generation function or key derivation function based on the serial number, which is 28 bits. So we mask off the top 4 bits to make sure that the function code is not included. And then we decrypt the serial number combined with a 6 in those first 4 bits. And then we combine that, we shift that over 32 bits and combine that with the same process, just simply changing the 6 for a 2. It's relatively simple and straightforward, but as you can see, if you do know what that serial number is and the manufacturer key, then you can derive those shared keys. So what attacks have been tried against Keylock environments or ecosystems? One approach has been to perform cryptanalysis, and they have found specific weaknesses primarily due to implementation flaws. Their calculations, based in 2007, were able to reduce the effort to crack a single transmission down to approximately 2 weeks of FPGA-assisted calculations. Not really practical, depending on exactly what it is that you're trying to approach or trying to attack. Another approach, which has been much more effective, is to perform side channel attacks. In this way, they performed differential power analysis by monitoring the use of, or the power use of the receiver or the transmitter while it's performing its cryptographic operations. They were able to determine what values the keys had by looking at the precise power consumption using very accurate monitoring systems. And in this way, they were able to extract the key, the unique key from a transmitter, or the manufacturer key from the receiver. And this is ultimately a complete break. However, it does require you to customize your attack for the particular transmitter. Well, if you attack a single transmitter, you get one key, and you would need to repeat it for each transmitter. And then you would need to customize your attack and understand the implementation of the crypto algorithms on each receiver, as well as performing it for each CPU architecture or implementation for each different manufacturer. So depending on which CPU family or microprocessor family the vendor is using, you may need to conduct this attack several times. And then in 2015, Sami Kamkar demonstrated replay attacks, which supposedly should be impossible, but he realized that if he jammed one's transmission while recording it, and you can jam, you can allow the first 60 or so bits to be passed through and then override the last 4, which you can reconstruct yourself, so you don't need to know what they were. Then jam and record a second transmission while replaying the first. And in doing so, you would end up with a single transmission that you could use at a later point, while the user has walked away from their car. The problem with this is that it only gets you that single opportunity to reuse your captured transmission and probably a limited window to use it in. Of course, if you haven't used it by the time the car or the driver comes back and unlocks their car, that captured transmission is immediately invalidated. But there's another attack that you could possibly perform that doesn't rely on differential power analysis or super complex equipment and so on. It doesn't actually require a whole lot of deep technical knowledge either, which is good in my case. And that attack is to actually extract the firmware from the receiver and reverse engineer it to retrieve that manufacturer key. Now, of course, in most cases, this shouldn't be possible if the vendor has set up their receivers properly. In my case, it turns out that they hadn't disabled debugging, and it was possible to extract that that firmware. And so I was able to extract the firmware and started learning how to use Ghidra, which has support for bare metal ARM binaries. In this particular case, the CPU in question is made by ST Microelectronics and STM32F103. So Ghidra has support for ARM binaries, and so I started out loading it up into Ghidra and trying to make head or tail of what was going on. It was quite a learning curve, never having done any reverse engineering at a machine code level before. I decompiled Java, but that's not the same thing at all. Fortunately for me, Ghidra has a mode where it can decompile the machine code into approximate C code, and that certainly made my life a lot easier. One very useful tool, which I found quite helpful, was SVD Loader. What this does is it automates the complete generation of peripheral structures and memory maps for microcontrollers. By parsing the system view description files, SVD Loader is able to annotate all the peripherals of the controller, simplifying reverse engineering significantly. And what it does essentially is it translates memory offsets into peripheral names and labels. So for example, you can see that the value DAT 4000000 ORed with 0xC, etc., is actually part of the Bluetooth controller of the particular chip being used in this example. While it ended up not leading me to the relevant functions, nonetheless, it did make understanding what I was looking at a lot easier. The next approach was to try following the code based on the strings which were displayed while enrolling a transmitter. In particular, press any key to enroll was the key, so I tried to follow it by looking at references to the string press, and went down a rabbit hole and ended up not being able to find it. I think the problem was that I ended up down a rabbit hole of display-related code rather than finding anything using the radios. And I also suspect that the radio-related code was interrupt-based rather than being part of a continuous loop. So even though I was looking potentially in the right place, I ended up not finding it this way. Then I ran into a blog post by a guy named David Lodge, Tips for Reverse Engineering Crypto Code, and this was invaluable to me, although it did take me down some unproductive rabbit holes initially. So always looking for strings and constants. Strings didn't help me, but looking for constants absolutely did. Make guesses about the original source, or if you can find it, look for the actual source code. The good news is that the source code for the key lock algorithms have actually been leaked on the internet. It is supposedly protected by non-disclosure agreements, but you can find it out there. And there are a number of independent implementations of those crypto algorithms. So that helps you to avoid making those guesses. Although it still doesn't entirely help you know exactly what is in the firmware. So I ended up looking for constants in the algorithms that I found online, and that did take me down a number of rabbit holes. The constants that I was looking for simply didn't exist in the firmware at all. And so that left me scratching my head. It turned out that because there are multiple implementations of the key lock algorithm, I was looking at a rather more refined version than the original manufacturer code, and as a result, the constants that I was looking for simply weren't present. The constants in the manufacturer provided code were present, and those quickly led me to the relevant functions. So I'm not going to go, as I mentioned, I'm not going to go through the details of exactly how I found the manufacturer key, because it's still in wide use, and there is no plan from the vendor on how to rotate it. I can imagine that this is a particularly complex problem. They've sold thousands of these remotes and receivers out into South Africa and out into Africa as well, and they don't actually have any way of getting hold of them, as well as reprogramming all of them would be an incredibly complicated task. So suffice to say, if a noob like me can find it, it was not too well protected. So, decoding the keylock code word. I first wanted to make sure that I could decode the incoming transmissions from the radio chip using my PC before trying to implement the algorithm in C in a microcontroller. It just is a much more friendly development environment. And so what I did was I used a cheap logic analyzer to tap the line between the RF decoder chip on the receiver board and the microprocessor. And after much trial and error, I was able to isolate the actual transmissions from the surrounding noise and start trying to decode them. I used the SIGROT project's PulseView UI to look at the results. Now, there was no keylock decoder implemented, and so I had to implement my own. Initially, I was trying to decode an entirely incorrect portion of the capture. I finally managed to correlate the transmissions by soldering a wire to the transmitter button and monitoring that line at the same time as the radio receiver. By focusing on the portion where the line was high, I was able to identify the actual transmission and start trying to decode it. Eventually, I had a Python decoder implemented that gave me the same results as the original vendor firmwares for a specified transmission. And this will be open source when I get around to submitting a pull request and shepherding it through the process. As you can see, the individual nibbles can be extracted. 0EC8, etc. But then those need to be read backwards because it is transmitted least significant bit first. And then you can see the serial number and then the button that was being transmitted, or the buttons that were being pressed. So that corresponds fairly closely to the diagram provided in the datasheet. Once I had a working decoder, I then had to try and figure out how I was going to implement this on the hardware. I went down an initial rabbit hole looking at libopencm3, which is a firmware environment for a number of ARM-based microprocessors. While it does provide a bunch of drivers and a whole lot of useful peripheral drivers, it would still have been quite an onerous process to re-implement based all of the functionality that I wanted for managing the remote receiver, as well as the relays and the buttons, etc., that existed on the existing hardware, as well as things like over-the-air updates and such like. And so I came across a project called ESP Home, which is a system to control ESP8266 and ESP32 microprocessors using simple configuration files. ESP8266 and ESP32 are microprocessors that have got built-in Wi-Fi interfaces. And so you can interface with these from the rest of your Wi-Fi network. However, so this looked rather attractive, but unfortunately this is a very different beast to the STM32F103 ARM-based microcontroller on the complex receiver that I had. Fortunately, there is an Arduino implementation for the STM32 family of chips. And with a little bit of work, I managed to get ESP Home running natively on the STM32 and on that complex receiver board. One reason I think that this was a good decision is that ESP Home actually has built-in support for transmitting and receiving infrared and RF remote control signals. And this ended up saving me quite a lot of time. While Keylock was not amongst those implemented, actually implementing the decoder was a relatively simple matter using the existing implementations as a guideline. And as you can see, it only needed a fairly small amount of code to get ESP Home running on the STM32. And a bit more code to implement the Keylock protocol, to implement the encryption algorithms, and then finally to implement a programming algorithm for the Keylock transmitters that I had. And what this allows me to do is actually program a duplicate transmitter with my chosen serial number and derived key, as well as choosing the starting replay counter value. So a quick demonstration of what the ESP home system looks like. This is just looking at the serial output, the logs from the ESP home firmware running directly on the STM32 based complex receiver board. The orange block is purely to focus your attention on the important details. So you can see a text sensor being updated, both as the built-in button repeat occurs and is cleared, as well as when further buttons are pressed. In the leftmost colon-separated field is the serial number, then the button which is being pressed, followed by the counter value, and 2 status bits, battery low and repeat. So there's the serial number, the button, the counter value, which you can see incrementing A, B, C, and D, and then the 2 status bits. As you saw in the previous demonstration, it was possible to observe the transmissions picked up by the complex receiver using the USB serial port. Of course, that then requires a PC to be powered up and an additional program written to translate those serial output into Home Assistant sensor states. I decided that I wanted to have it as self-contained as possible and using as little power as possible. So this brings me back around to the ESP Home. I happen to have an ESP32 dev board, a development board handy, which brings us back into supported territory in ESP Home. The complex receiver board originally had a display board attached via the double row header between the program header and the mounting holes over here. The pins available on the header included power and ground, and fortunately also included a serial port. The remaining question was, what is the best way to take the ESP Home entities, things like switches, sensors, the key lock receiver, etc., and expose those to an external client? Well, ESP Home already had an API defined for connections made over TCP connections from Home Assistant using Google Protobufs. I figured it would be a relatively straightforward solution to implement the same protocol over a serial port and then write a client implementation that would map remote entities on the STM32 into the local ESP Home instance on the ESP32. In this way, updates from the STM32 would be sent to the ESP32 and forwarded on to Home Assistant, and instructions from Home Assistant, for example, to activate a relay, would be sent to the ESP32 and then forwarded on to the STM32. And finally, Home Assistant also has a predefined interface for RFID tags, which essentially presents a string representation of the tag ID. This sounded quite similar to what we're dealing with the key lock transmitters. And so a few hundred lines of code later, I had a client interface, a client API implementation. Well, it's incomplete because I only implemented the sensors and other entities that I actually needed for this project. So things like covers, garage doors and blinds and so forth are not supported, for example. So here is a demonstration showing the Home Assistant receiving transmissions from the receiver. If you look on to the right, you can see the button incrementing as well as the counter incrementing. And then if we go to the RFID tag interface, we can see a similar approach. You can see the serial number and the button without the counter. the counter value was removed simply to make it easier to map a constant value rather than a constantly changing value to actions in Home Assistant. This is the logic that is followed. This is a snippet actually of the configuration file for the STM32 version of Home Assistant, of ESP Home. The remote receiver calls the onKeylock function with a value representing the decoded fixed and hopping portions of the transmission. So if the keylock decryptor, i.e. the implementation of the crypto algorithms, can decrypt the transmission, then format the details, the serial number, the button, the counter, and the various flags into a buffer and send those to Home Assistant. This is an example of the configuration of the HCS 301 transmitter and a script to program one with the specified serial number and key, using the normal keygen key derivation function and a serial number of 0. In this case, I'm programming serial number of DA342B with an initial sequence number of 0. So some outstanding features. I haven't yet implemented persistent recording of counters and replay detection. That needs an implementation of a storage API for the SPI EEPROM, which is already on the board. I've done the design of the storage format, which will support 4,096 transmitters with up to 14 functions each, as well as logging of up to 8,000 events within the EEPROM. The current manufacturer firmware will only log to an SD card, which is not necessarily a problem, but it is an additional component. In addition, the client API and the server occasionally get desynchronized, and at the moment that does not recover gracefully, so I need to fix that before this could be a robust deployed setup. And then enhancements to the client API to implement the remaining entity types that I haven't yet implemented. And then finally, there is a problem with the HCS 301 transmitter algorithm, and I'm not so sure whether it's a problem with the algorithm or not, because I've confirmed that the value which gets programmed is in fact received by the transmitter, because you can read back the value during the programming sequence. You simply can't ever read it again after that. So the problem that I've encountered is that trying to program an initial sequence number greater than about 60 or so ends up with a corrupted value. And so the value that you've programmed is not the next value used when starting a transmission. I suspect that this might actually be broken silicon. I'm pretty sure that 99.99% of vendors simply program a sequence number starting at 0 and have never encountered this bug. But yeah, that is something that I'd really like to try and solve, because without it, it's a bit more difficult to actually transmit or to create a forged transmitter. So the code for this is available in my ESP Home fork. There are 3 branches: the code for the STM32, the code for the keylock, and the API client. If you want to try and replicate my work in your own environment using a complex receiver, you'll probably want to merge those 3 branches together. have it all function on that STM32. They were created separately because they are pretty much independent pieces of work, and the Keylock and API client work does not depend on the STM32, or they're completely independent, in fact. So that is the summary of my journey through the Keylock environment. Thank you very much for coming along on this journey with me. And if you have any questions, I will be in the chat for a while so that I can answer them. Thank you very much.
Hey everyone, and welcome to my talk today. In order to have future foresight, it requires that we look back at events that have already taken place, and that is what I'll be doing in my talk today. I'll be presenting a retrospective of 2021 and do some analysis and insights of some of the major security news and events that have taken place over the past year. Just a quick introduction about myself. I'm a cloud architect. I specialize in security and enterprise cloud architecture, and I help large organizations adopt AWS. My research interests include privacy, surveillance, encryption, and disinformation, and I'm also involved in policy advocacy work on these topics as they relate to national security interests. I'm also a bit of an aerospace nerd. My Twitter handle is @JaredNordia, and my blog is @criticalvoid.com. In my talk today, I'm going to be talking about the year of the supply chain. 2021 has really been the year of the supply chain, with many supply chain issues as well as supply chain attacks. I'll also be talking about some other issues, for example, about the Apple CSAM debacle, disinformation, the Cybersecurity Review Board, ransomware trends, as well as the software bill of materials as well. 2021 was really a challenging year for the supply chain. Fire, droughts, geopolitics, and the pandemic really stretched the supply chains to their breaking points, and there is a worldwide shortage of rubber, lumber, a specific type of chlorine due to a massive fire at a production facility, a shortage of semiconductors and chips, which have had a massive impact in the automotive industry, as well as in the shipping and transportation industry as well, where there isn't enough containers, as well as very long wait times at the various ports. Obviously, we all had a joke at the Ever Given that got stuck in the Suez Canal, but really the big challenge here is that due to the pandemic, consumer spending has shifted away from services to consumer goods, which has created a massive demand for these consumer goods. Texas also had a massive issue earlier this year where they were not able to meet the electricity demand with the supply due to cold weather, and they were actually 4 minutes away from experiencing a total grid collapse. In the digital world, we had a number of supply chain attacks, and probably one of the largest supply chain attacks that ever took place against SolarWinds, which really started out with the FireEye breach. In December of last year, FireEye detected a malicious activity on its network. A user account that had newly registered a MFA device, which was also used as a secondary device, triggered an initial alert, which then triggered a massive investigation to kick off. FireEye knew immediately that a nation-state actor was behind this breach due to the tradecraft that was being used. During this investigation, FireEye honed in on the SolarWinds deployment, and they reversed engineered the code to actually find 4,000 lines of malicious code that was added into SolarWinds. For those of you that are not familiar, SolarWinds is an IT service platform that provides remote management and monitoring, as well as some other features for IT service management. And due to its specific function, it actually requires privileged access to some of these systems in order for it to work. The main issue with the SolarWinds supply chain attack was that in their CI/CD system, when they released software, one of the components was a Jenkins machine which was exposed to the internet with the password of SolarWinds 123. Adversaries were able to break into that Jenkins machine and then able to add malicious code which would create C2 channels as well as web shells on victim infrastructure. From a timeline perspective, in August 2019, the initial command and control setup was done. In October 2019, a dry run of the attack took place, and in December 2019, the first payload with Cobalt Strike was actually detected. A lot of commentary has been made in the community about the fact that they were using Cobalt Strike, given that a lot of security tools can actually detect Cobalt Strike, and it would seem a bit unintuitive to actually use Cobalt Strike in an attack of this nature. Malware known as Sunburst was actually then injected into the Orion platform in February of 2020, and in March of 2020 the first signed backdoor version of the SolarWinds platform was actually released to customers who received it through an update process. At the end of December, FireEye announced that they had been a victim of a nation-state attack. FireEye disclosed the supply chain attack to SolarWinds, who thereafter then notified their customers as well as filed a SEC statement for their shareholders. What's very interesting, the finger was pointed at this being a Russian operation very quickly. However, President Trump at the time insisted that this was a Chinese attack rather than a Russian attack. And at the end of December 2020, Microsoft actually announced that some of its source code had actually been breached as part of this. And as the new year started, so that would be the beginning of this year, a lot of people started realizing that this was going to be a fairly significant breach, and a joint statement by the FBI, CISA, the National Intelligence Office, as well as the NSA really alerted people to this significant breach. In terms of impact, this attack allowed adversaries to get access to Microsoft source code, as well as to the SAML signing tokens for 40 companies, which allow attackers to log into services and infrastructure directly without MFA. In most cases, when you log into something with SAML, that's typically done by some kind of identity platform, and by having those keys, you effectively can bypass that infrastructure, which would also then enforce MFA in the process. The access gained by the adversaries allowed them to move laterally in the customer environments of Microsoft customers as well, and 30% of the private and government businesses affected by the breach had no known link to SolarWinds. A number of US agencies were affected by the breach, and up to 18,000 private and public entities were directly affected by the supply chain breach. Microsoft President Brad Smith was ordered to testify in front of Congress, and he was actually grilled about Microsoft's licensing policies, where a lot of logging features, for example, are not available on the lower tier plans. This is one of, I think, Microsoft's big failures from a licensing perspective. And on a side note, I think if you compare this to AWS, for example, this is one area where AWS actually does really well, actually. Another supply chain attack that we learned of is CodeCov, which is a code coverage tool. Adversaries were able to use a vulnerability to gain access to a vulnerable Docker container, where they were able to change the IP address of a specific configuration file, which allowed them to pull sensitive environment variables out of CodeCov's customers, which included a number of big names, including HashiCorp, The Washington Post, Monday.com, and Uber. Some companies had limited exposure. For example, HashiCorp only had its PGP key exposed, whereas other companies had more sensitive credentials exposed. Another interesting supply chain attack was that on Kaseya VSA. Kaseya VSA is a remote monitoring and management tool primarily used by MSPs to manage customer networks. A vulnerability allowed an authentication bypass on the platform, where attackers could install malware on the hosts managed by the specific platform. Affected systems were encrypted with ransomware from the Revil Group, and the Revil Group claimed that over 1 million systems were actually infected, where this was actually disputed by Kaseya. They said that between 800 and 1,500 systems were actually impacted. One of the most notable impacts was a Swedish retailer called Coop. 800 stores had to close down due to their payment systems not being available, and this actually had an impact on the food supply chain in some small villages where Coop was the only retailer, food retailer in that area. Another interesting attack was on Travis CI. A vulnerability in Travis CI allowed environment variables to be exposed during the build phase. This meant that open source code could be used to actually retrieve environment variables of systems using Travis CI. And to make this even worse, Travis CI actually tried to hide this from their customers once it was actually disclosed to them, which I think is completely unacceptable. The next attack was against the Linux kernel. An assistant professor at the University of Minnesota actually tried to fix real bugs in the Linux kernel, but in the process of doing so also intentionally introduced new security flaws as part of a research project. This led to the University of Minnesota getting banned from the development on the Linux kernel, as the open source community found that this behavior was completely unethical. One of the other interesting things from a supply chain perspective was compromised packages. So there have been a very large number of new NPM packages registered. I think after the SolarWinds breach, everybody wanted to get into the supply chain attack, and you can see on the right hand side there how many new NPM packages were actually registered at the beginning of this year following the SolarWinds breach. And what attackers would do is they would use compromised repositories and accounts to add malicious code to popular NPM packages, and this included UAParser, RC, Koa, and WebBrowserify, which together have over 30 million downloads per week. Typo squatting was also on the increase this year, with over 3,600 packages on PyPI with similar names that also contained malicious code. Another interesting discovery made earlier this year was this issue of dependency confusion. This is a risk where IDEs and package managers are unsure whether to fetch a package from an internal repository or external repository. So you could tell a system to go get a specific package, and if it fetched the wrong one, for example from an outside source, you could actually introduce malicious code into the system by doing so. A researcher actually managed to do this into Apple, Microsoft, and dozens of other companies. Some other notable supply chain attacks that have taken place in the past: an attacker distributed a version of Xcode which was backdoored, and what it would do is whenever new iOS applications were created, it would actually inject this malicious code into the iOS app that Xcode then created. This resulted in thousands of compromised apps on the iOS App Store. In March 2016, a popular open source BitTorrent client transmission was compromised to include macOS ransomware in its installer. In June 2017, the NotPetya malware was actually spread through a breach at a Ukrainian software company, and this then turned into a wormable exploit that then spread worldwide and affected many organizations in the process. And a few months later, Avast CCleaner tool was also compromised and used to attack large technology and communications companies worldwide. Another interesting supply chain attack, which was actually not done by malicious actors but rather by law enforcement, the FBI actually managed to shut down and arrest the operations team of EncroChat and Phantom Secure. These are platforms used by the underworld for drug trafficking as well as other nefarious activities. And after the FBI did this, they realized that there would be a massive hole left in the underground market for a secure messaging platform. And they had this brilliant idea of creating their own backdoor secure messaging platform that they would want to share with all of the members of the underground. So that's exactly what they did. They teamed up with the Australian Federal Police and Europol to basically set up a bunch of secure backdoored phones, and they then created a new service called Anom that was only available on purchased devices. They already used the trust networks that were already present in the underworld, and they ensured that the system was only invites only, and they used influencers in the underground to basically spread these devices around. And the scarcity made people believe that this platform was actually really secure. What they also did is they used clever cryptography so that the messages were end-to-end encrypted, but they had the master key so that they could intercept and decrypt all of the messages as they were being sent around the world. And the FBI let the service run from 2018 to 2021, and during this period 200 million messages were intercepted from 11,800 devices in over 90 countries. And here's a map. You can see the law enforcement agencies in North America, Europe, and Australia and New Zealand were involved in this operation. When arrests started to take place, they seized a large amount of currency as well as phones. You can see a specific drug trafficking arrangement taking place here. They also then went to seize the drugs that were being currently trafficked, and you can see a number of interesting containers as this occurred. More than 800 suspects were arrested, and more than 40 tons of drugs were actually seized as part of this operation, as well as 250 firearms were seized. One notable thing about this is that the FBI routinely complains that they are going dark due to encryption, but one thing we can actually take away from this is that actually these initiatives allow law enforcement, to go after their targets without requiring backdoors in on our phones. Moving on to ransomware. Over the past few years, ransomware has really exploded in both the number of victims as well as the amount of money paid to ransomware groups. The infection mechanisms have changed somewhat. In the past, it was always a system compromise, whereas today, phishing as well as software vulnerabilities are becoming the primary entry point for ransomware. The Internet Crime Center has actually noticed a 62% increase in reporting of ransomware attacks based on the first half of the year compared to the previous year. And you can also see some of the common variants that are affecting people around the world. One thing that people don't often note is how organized these ransomware groups actually are. They actually have affiliate programs that they market, and this really allows them to scale appropriately. And when we start looking at ransomware as a service, many people are not actually aware that, there's actually the ransomware group which creates the actual malware. There's the affiliates which actually then go infect and attack people, as well as deal with the operations of running the ransomware. And typically during an attack, the ransomware group would give an affiliate software that has a unique ID so that the ransomware group can actually track the targets that they are hitting. And when a victim is actually infected with ransomware, the victim would pay the affiliate, which would take a 75 to 90% cut of the ransom, and the ransomware group would get a 10 to 25% cut of the ransom. So sometimes the ransomware group and affiliates will actually work together when they go after a large target. And sometimes the media thinks that both the ransomware group and the affiliate is actually one entity, when it's two completely separate entities. And this can lead to some interesting factual errors when they report on these stories. One of the benefits of having this affiliate model from a ransomware group perspective is that they can scale their business to have multiple affiliates and therefore a lot more targets. One of the other things the ransomware group does as well is that they actually use master key encryption so that the ransomware group has the master key, so that when affiliates go attack victims, and if they were to attack a high profile victim, the ransomware group would be able to offer a decryption tool to the victim, bypassing the affiliate in that case. And then many affiliates will actually use multiple variants of ransomware from different groups to try evade detection from law enforcement, as well as some ransomware groups don't allow affiliates to attack certain targets. So for example, some ransomware groups won't attack hospitals, while others have no problem in doing so. One of the interesting supply chain attacks from a ransomware perspective that took place was the attack against Colonial Pipeline, where an unpatched legacy VPN was used by the DarkSide ransomware group to encrypt all of their systems, and they demanded a $4.4 million ransom. The Colonial Pipeline processes 45% of all of the fuel in the US. And this led to a number of fuel shortages as people were hoarding fuel, including some unintelligent people who, for example, this person on the right-hand side of the screen who used a top inside his pickup truck and then filled it up with fuel, which is not a very smart thing to do. After this attack had taken place and the Colonial Pipeline had actually paid out the ransom, $2.3 million went to the affiliate and $2.1 million went to the DarkSide ransomware group. The Justice Department was actually able to seize and recover $2.3 million of the $4.4 million ransom payment. Another large ransomware attack was against JBS, which is the world's largest meat processor based in the US and Australia. The REvil group was behind this, and they demanded an $11 million ransom. Last year I spoke about somebody that passed away after a ransomware attack hit a hospital, which actually delayed treatment, and a subsequent investigation actually turned out that the patient died of other causes, although the ransomware incident was actually a factor in the death. What came to light this year was actually the first death that's actually almost directly attributable to ransomware. An expectant mother went to a hospital to deliver her baby, and she was not aware that the hospital was actually in the process of recovering from a ransomware attack. The ransomware attack took out the IT network that the hospital was using, and this IT network supported vital monitoring systems that would look at fetal vital signs, and this was not communicated back to the nursing staff who was looking after this mother-to-be. And they were not aware that the baby was actually distressed, as the umbilical cord was actually wrapped around the baby's head. And this led to severe brain damage, and the baby then passed away 9 months after birth. This came to light this year because the family is currently suing the hospital, because they argue that had they known that the hospital was under a ransomware attack, they probably would have gone to another hospital. The response from the federal government to ransomware has been quite fierce. The FBI and State Department have offered a reward of $10 million to the DarkSide ransomware group, as well as a separate reward for $10 million for targeting the leadership of the REvil ransomware group, and an additional $5 million for information of the affiliates or partners. One of the interesting things that happened was that Paul Nakasone, who's the director of the NSA and the commander of Cyber Command, actually spoke at a recent conference saying that, in the past the FBI always dealt with ransomware because it was criminal activity. However, when ransomware starts touching critical infrastructure, it now becomes a national security issue. And if you read between the lines here, what he's actually trying to say is he actually believes that the government should actually allow intelligence agencies around the world, including the NSA, to actually go after these ransomware groups. And Cyber Command actually took out a bunch of infrastructure from a number of ransomware groups, including DarkSide, actually after this event. One of the other things that the government has done is they've set up a number of resources, including a website where people can get immediate help during an incident if they need to. They also went after the people behind the Kaseya VSA breach. One of them has been arrested and the other one is wanted by the FBI. In the indictment, they claimed that these two affiliates they were able to get $6.1 million from the various attacks that they were involved in. Earlier in May, President Joe Biden actually signed an executive order to improve the nation's cybersecurity. As part of this, they wanted to improve the software supply chain security, as well as incident response, as well as the security posture in the federal government. In 2018, CISA was actually created, but they realized that they actually need to go further than that. So the Office of the National Cyber Director was created. Biden hosted a number of tech CEOs at a security summit to discuss how they can actually improve cybersecurity. And when Joe Biden actually spoke to Vladimir Putin, he actually warned him that Russia needs to take action on these groups as well. The NSA released Kubernetes hardening guidance, as well as guidance for securing 5G cloud infrastructures. They also put out guidance on how to embrace a zero trust security model, and they really hope that many US government agencies will actually start migrating their architecture into a zero trust model, which would have a significant impact on the nation's cybersecurity posture. One of the other initiatives is the creation of a software bill of materials. So the idea behind this is to manage vulnerabilities, to have software inventory, software licensing, and supply chain data, as well as tracking component metadata in enterprise software. And the way that this would be done is whenever a new piece of software is released, all of the high-level components are detailed in this document. What the version is, other identifiers, the dependency relationships, and this would effectively allow these systems to be able to track when a specific component is actually vulnerable, what other systems could actually be affected by that vulnerability. At the Security Summit, Google actually committed to securing open source. So Google already has programs in place to actually improve the security of open source software, but they've committed a whole bunch of money to actually take this even further. One of the big highlights of the executive order on national security is the formation of a cyber security safety review board, and the purpose of this is really to create a board that can really investigate cybersecurity incidents. So when a plane crashes, that is typically investigated by the National Transportation Safety Board, or the NTSB. They're one of the most trusted government organizations in the world, and their primary purpose is to investigate transportation accidents across aviation, railroad, highways, marine, and pipelines, and to make safety recommendations where needed. They've completed over 150,000 accident investigations and have made 15,000 safety recommendations to 2,400 recipients. One of the main goals of the NTSB is to determine not just what happened, but why it happened, so that it doesn't happen again. And the NTSB is actually part of a worldwide group of agencies that do these kinds of investigations, and a lot of them have bilateral agreements with one another in order to investigate various accidents, especially aviation accidents. And we really need something like the NTSB for cybersecurity. One of the problems that we have in cybersecurity is with that when breaches take place, we often get second-hand or third-hand information about what actually happened, and often the information that is shared is often actually just the the indicator of compromise and or the attack vector, but we don't actually get any information beyond that. And what we really need is, for example, if an attack took place and there was a monitoring system and the monitoring system didn't detect it, why it did it detect it, and if it did detect it, and somebody wasn't notified, what why wasn't that the case? And we really need to get visibility into these kinds of failures if we want to move forward as a cybersecurity community. These kinds of investigations exist in many industries, but until we actually get a really concrete solution for cybersecurity, we're going to be kind of in this place that we have been in the past. So the NTSB has a very formal process of how they investigate incidents. So when an accident occurs, they establish parties to the investigation and investigation protocols. They gather all of the information that they can. They'll then actually brief the media, where they hand over this factual information that they have at the time to the media. They will then hold investigative hearings to get any additional information, for example, from the vendors, etc. And once all of this has been completed and the investigation has been completed, they will actually meet to finalize the probable causes and safety recommendations, after which the report has been released. And just to give you some examples of these reports, in 2010, an A380 had a fan blade out event that actually caused shrapnel from the engine to actually sever the electronic trunks in the aeroplane, which made controlling the aeroplane fairly difficult. And it was only due to proper crew resource management that the pilots managed to land the plane safely. And interestingly enough, crew resource management was actually something introduced by the NTSB many years ago to help decision making in cockpits. One of the findings of this incident is that when those cables were actually severed, the pilots received over 400 alerts in the cockpit, and this was a problem for them because they were overwhelmed by the number of alerts. So various system changes were made to make that easier, as well as the fact that those electronic cable trunks are no longer run together. They actually are separated now. And it's not just big accidents that need to be investigated, but it's also the near misses as well, where, nothing major happened, but there are always lessons to be learned from, near collisions or near mistakes or near accidents as well. Another example is the Miracle on the Hudson. So a plane departed New York airport in 2009. It flew into a flock of birds, which resulted in dual engine failure. The aircraft was actually ditched in the water. Everybody was rescued and there was no fatalities. What was observed during the investigation is that pilots can't actually practice water landings in a simulator because it didn't have the capability to do so. And many pilots thought that if you actually landed a plane in the water, everybody would actually die. So one of the safety recommendations that came out of this incident was that simulators must allow pilots to practice water landings. Earlier this year, a Transair cargo flight that departed Hawaii had a dual engine failure. The pilot successfully ditched the plane in the sea. They were rescued by the Coast Guard. They never had any injuries. But an interesting question to ask is, had they not been able to train in the simulator to do the ditching, would this event have turned out any differently? And here's just some images of the NTSB doing the recovery. They actually pulled out the plane about 2 weeks ago. You can see the front part of the plane in this image, as well as the rear section. And the reason this is so important is to actually have a feedback loop in the industry. So the NTSB reports are often used in airline training programs so that pilots can learn from mistakes that have taken place. And there's also a dedicated YouTube community of YouTubers who actually take these reports and actually make really high quality videos from those reports. And even if you're not interested in aviation, these videos are still quite interesting. And it's not just aviation, this expands across engineering as well. So if you studied engineering, you probably would recognize this. This is the Howard Regency walkway collapse that killed 114 people. And this event resulted from a small design change that was done. and had obviously a tragic impact. The US Chemical Safety Board also investigates accidents in chemical manufacturing, and again, they use this as a lessons learned thing. If we want to move forward in the security community, we really do need an agency like this to be able to give us factual information as well as to solve some of the common challenges that people are having. I think one of the big challenges that a lot of companies have is enterprise crapware. One of my favorite conference talks is actually by Harun, who actually presented a talk around how broken the enterprise security business is at Virus Bulletin in 2019. And if you haven't seen it, I would recommend that you watch it. And a point that Harun makes is that, we suck at evaluating security products. And I think when such a review board is created, it will be able to shed light on what products actually do work and what actually products are actually bad. To close off this topic, I think we are in a sorry state when 8 of the 25 most exploited vulnerabilities are actually in security gear. 30% of all of the vulnerabilities across the US government are actually in their security software and hardware. And until we start fixing the core issues behind this, I don't think we'll actually move forward from a security posture perspective. The next topic is disinformation, or how the supply of information has been twisted. Over the past year with the coronavirus, there's been a large anti-vax movement to undermine the rollout of the COVID-19 vaccine. They often will spread false, baseless claims with emotionally charged imagery and language to provoke an emotional response from the reader. And research done by the Center for Countering Digital Hate discovered that 12 individuals called the Dirty Dozen were responsible for 65% of all of the disinformation related to the coronavirus vaccine. And these individuals have a large following and have routinely, peddled these baseless claims about the coronavirus and the vaccines. And in doing so, many of them have generated a large amount of revenue by pushing alternative unproven treatments and cures for COVID-19. A lot of them have books and webinars and seminars that they have, as well as pills that they then sell. And this is obviously ironic because many people won't take the vaccine because they say they don't know what's in it, but they'll happily take a pill from an unregulated person, which I think is quite ironic. While disinformation around the coronavirus vaccine may pose a public health issue, the real challenge is when disinformation has been weaponized to spread false, baseless claims. For example, the theory that the US election was stolen. This led to real-world violence on January the 6th during the insurrection of Trump supporters, where the US Capitol was actually attacked in an attempt to overthrow the election. And this obviously raises, the issue of how do we actually, address these issues. There was a rather controversial op-ed in the New York Times about the limits that free speech should have. I personally believe in free speech. However, how do you actually go about combating disinformation while making sure that you don't infringe on free speech rights? And this is really a hard problem. This is really a hard problem to solve. Next up is the Apple CSAM debacle of how Apple, betrays its values. In the past, Apple has proclaimed that privacy is one of its core values and has routinely taken shots at its competitors such as Google regarding privacy. However, in August of this year, Apple announced plans to put content scanning technology on iPhones to combat child sexual abuse material, or CSAM. As part of this announcement, they also announced initiatives to combat nudity in messages. I'm not going to go into that. I'm going to focus on the CSAM issue. So how this would work is Apple would get a list of known CSAM material from the National Center for Missing and Exploited to children. They would compare the hashes of known CSAM images to images on a particular user's iPhone, and if the image matches, the photo is encrypted with a safety voucher and then is sent to Apple. Apple will verify the image hashes before sending it back to the center during that process. And then this would be reported to law enforcement. The response from the security community was swift and clear that this is a bad idea. It was really great to see the entire community really, agree on this. Even people that I typically disagree with actually, said that this was a terrible idea. One of the first problems is the hashing. So in the past, images were hashed with SHA-256 and MD5, and if an image was resized, re-encoded, cropped or slightly altered, it would generate a new hash. Apple tried to fix this problem by creating a system called Neural Hash, which looks at the content of the image in order to derive the hash. So even if images are slightly different or have slightly different color, the idea is that they would generate the same hash. Apple claims that there is a 1 in a 1 trillion chance of a hash collision, but there's no way to actually test that because the census database only contains a few million images. The second problem is around reporting requirements. So under Title 18, Section 2258, all platforms that allow user-generated content to be uploaded to a platform must report any material that could contain CSAM. And there are harsh penalties if a provider fails to do so. And this leads to a situation where providers would rather report an image as potentially being CSAM rather than take the chance and be fined for not reporting it. And this creates an issue in the way that Apple wants to actually use the system. So as an example, let's say you have a photo of two 18-year-old teenagers engaged in sexual activity. This is a legal image. It gets uploaded to a social media platform like Facebook or Twitter. Facebook doesn't allow nudity, but Twitter does. And the image is reported to the social media platforms. They're not sure if it's legal, so they take it down and they report it to the National Center for Missing and Exploited Children, and then this thing gets added to the database, which then obviously updates Apple's database. And if somebody was looking at this image, again a legal image, the image hash would match. This would then be sent to Apple. Apple would do the verification. They would send it back to the center, and the center would then notify law enforcement. And the law enforcement would then do a search and seizure warrant. And this is really where one of the big challenges lies, because even though the images were legal, now somebody is having a search and seizure done against them, and even though they are completely innocent, this whole process can sow distrust with neighbors and can cause severe reputational damage even though the person is innocent. And this is particularly problematic if, for example, the media actually then goes and reports about this investigation as well. The second, more problematic issue is around the fact that this content scanning technology can be repurposed for government surveillance and censorship. So China or Russia could actually force Apple to actually use this technology to censor images or for requests to bypass encryption. If we look at China, these are 3 images that are banned in China. Obviously, the comparison of Xi Jinping to Winnie the Pooh, the Tiananmen Square incident, as well as an artwork depicting river crabs, which is a play on Chinese words to mock communist rule. And what the Chinese government could say as well, these 3 images, are illegal, and anybody that have them, could potentially face legal repercussions as a result of that. And many people would say, well, these governments don't really have the power to do so. However, the evidence in the past has actually demonstrated otherwise. So earlier in this year, Alexei Navalny, who is the main opponent to Vladimir Putin, actually created an app for tactile voting, and the Russian government reached out directly to the CEOs of both Apple and Google to have this app removed from the app stores despite the fact that it wasn't violating any app store policy. And Russia claimed that refusing to do so would be treated as meddling in the preliminary election. Also, China has a very firm grip on Apple. In the past, they have removed a lot of apps from the App Store. The Apple was forced to put the iCloud keys for China users inside of China, as well as share quite a lot of data with the Chinese government. China is a key market for Apple, so even though Apple, even though there are human rights issues, Tim Cook is on record saying that, they have a responsibility to do business everywhere, including China. Earlier, last month there was actually a research paper published which highlights a lot of these issues that I've just spoken about, and these government requests could really be a real threat, and Apple can't claim that it is impossible once they actually release this technology in the wild. Another thing to kind of think about is that recently Australia passed a surveillance legislation amendment which allows them to force tech companies to help them with investigations. And again, they claim that this is meant to help deal with CSAM and terrorism. However, we've actually heard these arguments before. As revealed by the Snowden documents, a lot of these governments claim that all of these laws and signal intelligence capabilities are used to fight terrorism and CSAM, etc. However, the evidence actually opposes that in many cases. And the community has really been pushing back on this move by Apple. Apple, for its part, actually says that this is one massive misunderstanding, and this is just people are confused, they don't really understand what's going on, and I don't actually buy that. This is actually quite a serious issue. One of the things that really enraged the security community was the fact that an email sent by the National Center for Missing and Exploited Children after Apple had released this, basically congratulating and thanking them for doing this, had this infamous line where they say that the days to come will be filled with screeching voices of the minority, and this really made a lot of people upset, including myself, because if we believe in privacy and civil liberties, are we now a screeching voice of the minority? And this is a classic, if you're not for us, you're against us kind of argument, which I think is actually a load of rubbish. The community also then started putting petitions together. This was an open letter requesting that Apple stop the deployment of this content monitoring technology, and that Apple issue a statement reaffirming their commitment to end-to-end encryption. Over 8,500 individuals and 34 organizations signed this letter. The Electronic Frontier Foundation also created a call to action, and 15,000 people actually signed this petition, as well as 90 organizations co-signed this letter, which was sent to the CEO of Apple. Apple, for its part, actually relented and actually decided to put all of their plans on hold, mainly due to the fact that they didn't want this to overshadow the launch of the new iPhone 13. So they, put this on pause. However, what the Electronic Frontier Foundation did on the day of the launch of the iPhone 13, they actually flew a banner over Apple Park, to kind of protest this move by Apple. In closing, we shouldn't have to give up our civil liberties to fight CSAM or terrorism. We know from the past that these things have very little impact, and once you give up your civil liberties, you don't actually get them back. So this is no laughing matter. And with that, that's the end of my presentation. Thank you very much.
why the options pattern is great for security. Hello, my name is Dima Kotik. I'm an application security engineer at Security Journey. We provide training for all matters related to security that is for developers and by developers. I am obsessed with service reliability, and I'm also excited about Golang. Examples in this presentation will be in Go because I like it and they fit very nicely on the slide. There is my Twitter handle if you would like to have a conversation after this presentation. Today we have 4 goals that we would want to accomplish with our exploration of the options pattern. And those are, first, we're going to review the options pattern for complex object initialization. Second, we will discover the types of vulnerabilities that the pattern can help us prevent. Third, we will improve the classic paradigm to maximize the security, and we can do that very well. And finally, I hope this talk inspires you and other developers to adopt the pattern when it fits. There's much to be gained here. To get started, let's define the problem we're trying to solve. OWASP Top 10 for 2021, number 5, is security misconfiguration. Last year, this was number 6. So this particular problem has increased. It doesn't matter how strong your application is, how many different firewalls it has, and different analytical tools and testing tools, all the CI/CD magic. If it is misconfigured, it will be taken advantage of. And this category in OWASP testifies that this happens a lot more often than many other vulnerabilities that we are afraid of. Second, now OWASP has added a category called insecure design. I would argue that programs that can be misconfigured and are misconfigured are insecure by design, and there are some things that we can do about it to prevent that. So this is a prevalent problem, and attackers love this. You can have a situation where your program has a hamstrung cipher. It may be capable of using all the best ciphers, but it has support for some of the legacy ones, which were enabled by a faulty configuration. A short key was provided by mistake, or an insecure source of random. This happens, and to attacker, this opportunity is like a piece of candy. How often we have programs that have missing access controls, or a misconfigured access control that expected a certain user group that was left blank, and the program interpreted it as no access control at all. So an attacker who belongs to no group at all just waltzes right past all the access controls and accesses an endpoint that should have been secure. This happens a lot. We also have debug backdoors left in our services. We need additional instrumentation, we need additional observability in our services, and designing them and building them into our application can help us in the development stage. It is often the situation that they are left by mistake to run in production. The service is deployed, but all those additional helpers remained. And perhaps they were not supposed to be there because they were behind a feature flag or a little environmental variable called debug equals true. And it was set to true at the time. And now an attacker found a way to do whatever they would like with their service. This is just a few examples, but you can imagine so many more. All of those go back to misconfiguration. And you can see how easy it is for the attackers to exploit those opportunities. And so they usually check for those things first because it is the most power given to them with the least amount of effort on their part. The problem with security advice that's currently out there regarding misconfiguration is that it's not really all that helpful. We have basically two different categories of advice. One is we're called to stop misconfiguring services. Yes, double check everything. Don't make those types of mistakes, and I don't think that will really help us much because our services are more sophisticated than ever. There's more of them. Then there's the whole cloud layer, which is very opaque sometimes and difficult to work with. And also our teams are large and they're more remote. They span time zones and they span languages and cultures. And it's just a matter of time before somebody misunderstands, by accident loads an older version of the configuration file or removes a commented outline by mistake that leads to misconfiguration. And simply telling people to stop doing it is like telling them to stop being human. We are human, we will make mistakes. So it's good to be reminded, but it's not really practical business strategy. The second one category is also the call to use a scanner of some sort. Policy validation, policy-based validation, or perhaps a static analysis tool, a dynamic analysis tool. We have hundreds of configuration validators these days, things that are based, for example, on Open Policy, Agent, or QLang. You can run configuration files through validators written for policies, right? But the problem is, for you to catch misconfiguration, you need to forecast what the problem is going to be. The tool needs to know the problem ahead of time, or the person writing the policy needs to know it. And the cost of discovering a misconfiguration is tremendously expensive. You already lost your data, you already compromised your users, and now of course you will write that policy, but that may be too late. So this is great. We should be using scanning tools, but we need to remember that they catch mostly the most obvious and egregious misconfiguration cases, but when we have custom solutions or we combine multiple solutions, there's just no way to foresee every different way something can be misconfigured and how configurations interact across boundaries. There's just no way. So the question here really is, can we do something engineering-wise to help with this problem? And the answer is yes, we can. Enter the options pattern. So what is the options pattern? The options pattern is a flexible object provisioning strategy using a list of independent object modifiers. So let's imagine that our package or our class is an engine, and we're going to just go and take it through stages of applying different tools to it. And each tool is only designed to tweak one or two parameters to get our engine ready to run in production. Each tool is narrow in scope, and each tool is applied only once. This is the basic idea behind the options pattern. To grasp it, let's go back to a Java classic, which will help us understand how this whole thing works. And the Java classic is, of course, the builder pattern for object initialization. The options pattern works similarly on the surface, but there are some significant differences that have ramifications for strong software design and security. So in our first example, here's an example of using a classic builder pattern where we have, say we want to have a bank account builder, and it will be a class that will construct another class called bank account, and we will supply by calling methods different parameters to our builder, and finally we will call the build method and have our bank account. In the second example, it's the same idea but using the options pattern. And the difference here is that instead of using a class, we will use a constructor function that will take a list of object modifiers, a list of options. And by convention, we start those with the word with, and we'll take those parameters, each one of those options, typically a closure. We'll tweak that parameter for our bank account, and there's no need to run the build method because the options initialization step, the constructor will apply the series of those modifiers and return the result. So the options pattern is kind of like a cousin of the builder pattern. It's superficially very similar, but one way to differentiate them is to think of the constructor pattern as one object preparing another. For the options pattern, the object is prepared using a list of modifiers, a list of options. Those are typically closures. Let's look at the classic. This is how I first learned functional options from the Go community, and it took me a while to appreciate the value of it. This is just a really simple example. First, we will define a type called option, and an option will be just a function that will take a pointer to the thing we're trying to construct. In our example, it's a bank account. And once we have defined the type, let's create one option. We can make as many as we want, but let's create one option and call this option with email. With email, we'll take a string and return an option. This is a closure, second order function, right? And so it will return a function wrapped or hidden inside another function. And inside the other function, we will actually take our object B, which is bank account, and we'll apply that supplied email to our parameter client email. Please note that, of course, in Golang, client email is with a lowercase letter, and that means that it is a private parameter. When we're using options pattern object initialization, we want to protect our private parameters and not make them accessible by external modification, right? So we don't want people to go and change our values without going through proper modification channel, safe modification channel, which is our closure. So only we want to have access directly to the parameter. Otherwise, if people want to change, then they have to go through the option. And that's the main point here, right? So we keep those parameters hidden under wraps and private. Can we improve this pattern, this classical pattern, in any way? And we can. We can improve it by applying 4 classical failure conditions, safe or secure failure conditions. We want to make sure that if our program fails, there's 4 traits that it has in the process of failing. And those are that the failure is early, and of course, object initialization is about as early as you can. Your program is just starting, it's warming up. We want to fail safely, so there's no leaks or memory dumps or any kind of crashes that leave threads open or something like that. We want to have a safe failure. We want to fail explicitly, so the reason for the failure is known, so that upstream services can deal with the error, and so there's a way to catalog it and document it and maybe trigger an alert or response of some sort. So that has to be very specific. And finally, we want to have a singular point of failure. It is terrible to have to deal with a program that cascaded into a myriad of different failure causes when you have 5 potential problems that could go wrong, and you don't know. You just have like this giant log dump, and you're trying to figure it out, right? So can we use those 4 conditions and apply them to the options pattern? Yes, we can, and we must. The main point here is that insecurely configured services should not even start. If something can be misconfigured, it will be misconfigured. It's just a matter of time. Our engineering should be up to the task. It needs to be advanced enough to anticipate problems and to quit naming the reason for the failure, naming the exact reason for the failure gracefully, so the whole thing spins down and we know what to do. How do we do this with the option pattern? Well, there's a small adjustment that we're going to make to the classic, and the adjustment is this. To our type, when we define our option, we will also add a return type error. So now it's not just a function that takes a pointer to the bank account, it also returns an error. So our validation logic will be now inside our option. It's not just a setter method, it's not just doing a modification, it's also going to do some checking, some validation to make sure that the parameter is correct. So once we have added this capability, now when we create our option with email, we will return the same closure, but this time it has the capability of checking for errors, and we will validate the email inside the closure, for example, by using a regular expression, and return an error if it doesn't validate. In some languages, we can use, we can just throw an error. That's just a style question, right? So Go returns errors as values. I think that's better. but throwing is also an option. The point being is that this will translate into other languages nicely. This is just an example. But what you are doing is checking, is this parameter absolutely legit in every possible way? Can it mess me up somehow? And once I know that it can't, now it's safe to ascribe or to assign to our main object, and finally we will return a null, meaning that nothing went wrong if the execution went all the way to the end of the function. That's a safer options type. How do we use those in a constructor? Well, that's what a typical constructor will look like. We'll call ours new bank account. It will take a list of options called, we'll name it with options, and return a pointer to our bank account and an error. So our resulting bank account will be just blank. We're not going to do anything with it to start with. And then what we will do is we will iterate one by one through every provided option, evaluate it, apply it to our result, and if there is an error, we'll return it. And of course, when we're returning the error, we also should be wrapping it, so it is clear upstream that this is initialization failure, that there was not something that went wrong in the execution stage, it went at the initialization stage. This helps with clarity and the stability of our service. Finally, at the end of the constructor, we want to validate the result itself, but not the parameters. So what this means, basically, we want to check if mandatory parameters were set, if it has all the right things it needs to have, and then we can return it and return nil for an error. Not too difficult, very basic example. There is some boilerplate, but trust me, it pays off doing this when it fits. How does it pay off? What does this really get us in the end? Well, rigorous or well-designed, documented application of the options pattern allows us to deal with three different things at the very least. And those are invalid and insecure state, right? We don't want to launch an object with something that's nil or something that's misconfigured and just broken, incapable of carrying out a critical task, which could have security ramifications. The second one is we want to prevent failures originating in parameters. Those are actually very common because as programs get more sophisticated, a lot of times a parameter being passed is a behavior, like a cache, for example. So you're passing that to your object, and that can have a lot of complexity, and you have to ask the question, how was that configured? Who configured it? Who provided values to that parameter? Do I know if it works? Usually we assume that just because the interface was satisfied or just because the thing was given to us inside the program, so we think, well, if it came from inside our program, it should be fine. Well, no, it should be validated, right? There should be some basic checks, because otherwise there will be failure originating in the parameter that can affect the rest of the program. So we want to guard against it, and the options pattern can help with that. And finally, conflicting parameters. A lot of times what will really mess you up is not one misconfigured thing. It's usually an interaction between parameters that can undermine or cancel out another. And those are also difficult to detect because the configuration itself can look rather benign, and something that's obscure and not as noticeable can critically impact something else, another part of your execution. The options pattern can help with this. I'm talking about how wonderful this thing is, and hopefully I can convince you, but there is definitely usage criteria. We should not be using this everywhere. Where should we use it? Typically, I use it, if I do use it, maybe once per package, once per program, not more often than that. Whatever you're configuring has to be sophisticated enough. And there's three criteria you can go by to choose if you want to really work with the options pattern. And the first criteria is flexible behavior. So does your object change the way it behaves based on environment, based on the configuration values provided? Are you passing providers or drivers or caches or networking layer adapters or any kind of adapter to your object? If you are, there's flexible behavior. And that means those parameters with behavior should be validated. So you'll need the options pattern. Second, if you have some mandatory parameters but not others, or if you have a situation where the list of mandatory parameters can change circumstantially, right? So that's fairly sophisticated. And also, if they were all mandatory, you would be probably better off with something more straightforward, like a dictionary keyword initialization strategy, because that will be clearer, right? But if that's not so easy, right, that some are mandatory, others are not, the options pattern is probably a better bet. And finally, if you have entangled parameters. And what are those? It's a class of conflicting parameters where changing one produces a side effect that can cause problems or warnings or errors for another. Let me give you an example of what that would look like. Let's suppose we're writing a hypothetical asset encoder, and let's just put together an option for it. And it's let's say it's for an IoT device. It will be kind of something simple, not too sophisticated, but who knows. So we're writing it, and we're going to write an option called with block size and memory limit, and we're putting size and limit in the same option. And why? Well, here's the reason. Because size, block size, and memory limit have several conditions, several interactions with each other. They are intertwined. First, those are just three things I can think of from the top of my head, but if you thought about this problem or had to write an asset encoder, you can think of more, right? But first of all, the limit has to be greater than 0, and it has to be greater than size. The limit has to be a multiple of the size, because we don't want to end up with a block that's overflowing a buffer or underflowing a buffer in the end. Like that will just create a complex logic in the encoder itself. So to prevent that, we can just check, first of all, the limit has to be a multiple of the size. And third, we may have protocol constraints. Like we just, for example, know that in the protocol for this encoder, there's only 2 bytes for the block sequence, and that puts a limit on how many blocks total there can be. So those 3 things are significant issues and significant areas of interaction between those 2 parameters. So if you change size, a limit will be affected, and if you change limit, size will be affected. In low-level languages like C, those simple things are deadly, potentially, right? Missing this can result into a remote code execution, a buffer overflow, a DOS attack, a crash. I mean, you can just imagine just about anything, right? So even with stronger languages like Go and Rust, even if memory is not corrupted, the interactions between parameters can still unbalance it and toss the service over. So what are we going to do about it? Well, we'll write an option in such a way that we validate all those areas of interaction. We try to forecast them, threat model a little bit, and build that threat modeling into the code in such a way that when we finally assign block size and memory limit to our encoder, they were proven to be correct. They were proven to be safe. And then we return a null. You can see here right away that this also creates what we call self-documenting code. When the person is using your package, IDE will give them hints, right? So they start typing and they start selecting options. So they'll type something like, well, I want to change block size and memory limit. And they'll see by typing either one, as it comes up using the fuzzy search, that they go together. And the programmer may not understand the full extent of the relationship between those 2 variables, but just by consuming it this way through the IDE, they have a hint that they are connected. And this is documenting, this is hinting to another developer that those parameters are significantly connected. And this creates documentation that's implicit. It's very convenient and very helpful and more secure. Can we improve this even further? Yes, we can. We can improve the options pattern even more by adding option grouping. This can help us with isolation, clarity, and safety when we combine multiple options as one. And those options could be private or public. Let's look at how we would go about doing that. We will write a little helper, and we'll call it with options, that will take a list of options and return one option. Why would we ever want to do that? Because it's wonderful. I'll explain. So let's make that work, right? So let's make that option. We'll make a function that takes our bank account and returns an error, and we will iterate through every option and apply that option to our B, our main object, check for an error, and if there's no error, we can return. Well, this loop right there looks exactly like the loop we already wrote for the constructor. And we can just externalize it, right? We can pull that functionality out. So while we're at it, let's just replace the iteration inside the constructor by using our little helper with options, and not forget to include also the error wrapping to characterize the error as an initialization error. So this is a little bit of more boilerplate. Why? What's the point of doing that, combining multiple options into one? Well, this allows us to unleash our little helper and create option sets. And one of the best option sets you can have is called with default options. That's what it means to have a program secure by default, right? Is actually having secure defaults, and that means functionality that configures the object securely, but also singularly. How convenient is it to just find out what are the proper decent configuration values that I should be using with this class just by clicking on that list with default options, and then immediately I can see the entire list, the values that are expected, and it helps me decide what I might want to change, right? Or it helps me see what things are mandatory from a single location. That's excellent for clarity and security. With default options, it's great. Something else, you can also write an option set called with debug options. And those are wonderful. Why would we want to do that? Well, because we can write special unsafe private options. For example, like administrative backdoor that we don't want anybody just using frivolously. And we can hide that administrative backdoor option called with administrative backdoor. We can hide it inside an options set called with debug options. This way, it is entirely clear to the user of our API that this backdoor should not be used by itself. It should be used together with as a part of a set, and also allows us to attach instrumentation and all the other things we may need for debugging, trace logging, etc. together, because you'll never have a situation where administrative backdoor is deployed, but there's no logger attached to it, or anything like that. And while we're at it, while we're making those lists of debug options, why don't we also add a little check just to see if our service is running in production? Because if it is, we should be crashing it, right? We should not be deploying debug options into production. That makes it very insecure, and this way our little helper allows us to do it. And finally, we can also use our little helper for visual grouping and nesting. Sometimes three things are not really tangled, but it is helpful to see them on the same line and perhaps add a comment for clarity's sake. The little helper with options allows us to do this ergonomically and beautifully. Let's put all of this together so we can see the value. Let's look at some things that are more sophisticated than the simple examples that we were discussing. Suppose we're writing a hypothetical distributed secrets manager. Is that complicated enough? Oh yes, it is. This is hard to write. And since it's distributed, we will have peers, and we'll need a way to provide those peers to our constructor, maybe a peer discovery protocol, maybe both, why not? Also, we want to have a caching layer, because if it's distributed, it can be very impractical to wait for the round trip for the network layer, so we may want to have a cache. Redis is great, so let's just take a stack of Redis settings and wrap them in the adapter. We may want to do basic cryptography without revealing keys, and if we do, then we will need the option for providing ciphers to our secrets manager. So there's a way to control allowed ciphers. We want to also limit them to a certain list, and we can check for that list inside the option. And also, of course, the rotation window, right? What's the point of having a secrets manager if there is no rotation? It's absolutely critical. So we want to have a duration between which, at the end of which, we are expecting that the keys will rotate. And also we want to set max key lifetime. When you look at those two things, you realize that, wait a second, those two are pretzeled. Those two values have a significant relationship to each other. The rotation window cannot be shorter, cannot be longer than max key lifetime, right? Because if it is, we will have service outage because the key expired, but it wasn't rotated in. So it has to be shorter than max key lifetime. But also, max key lifetime cannot be too long. If it's more than like 5 times longer than the rotation window, then that defeats the entire purpose of the rotation, right? So it persists much longer and it increases the attack surface, and it creates other types of problems. But if we think harder about it, there's actually more potential problems. Because if we try to combine those two options, rotation window and max key lifetime, inside the same option like we did with size and limit in the previous example, it just will not work very well. First of all, that whole option declaration with rotation window and max key lifetime is very wordy. And then we realize that actually there could be more parameters that could affect us down the line. Maybe right now we can't think of any, but this could change as our secrets manager gets more sophisticated. But something else comes up. What if the cache invalidation was misconfigured? Our Redis cache, how is that configured? What if it's set up in such a way that the keys persist longer than their max key lifetime? We could have a situation where ghost keys are still in cache even though the secrets manager has already expired them. That would be a bypassed access control, and it's very easy to imagine a scenario where the misconfiguration causes it to persist for all eternity. So how can we address this? How can we do this securely? Well, we can lean on another initialization strategy, and instead of combining those into one option, we can just create another option. We'll call it synchronization strategy, and we'll take a list of keywords in a structure called synchronization settings, and we'll put the rotation window and key lifetime there, leave a comment because we expect that maybe there'll be more synchronization settings later. We can deal with them later. But now we can pass that synchronization settings structure to our Redis cache adapter and synchronize the two so they are the same, that the max key lifetime matches the asset expiration, the value expiration inside the Redis cache. The options pattern helps us think and threat model. Maybe we could call it something like options-driven design. Maybe not. I'm just kidding. Let's keep going. New hypothetical microservice, right? So we're writing a microservice, and of course we want to provide a host and a port. We want to have a port as an integer, so we can lean on the type system. We'll need a TLS configurator of some sort. Acme is great, so we'll just use that. And then, of course, timeout settings. Timeouts are so critical for microservices. If the microservice is getting tar pitted or is getting connections which cause it to respond very slowly, or to or the other way, to hold long sessions, it can bring down the whole microservice. It can affect other microservices. So we can externalize that as well by making a structure called timeout settings and divide it into ingress, egress, and idle session timeout. And that timeout can be actually shared not just with the HTTP stack, but with other parts of the microservice. So the entire a microservice is secured with all of its interactions, internal and external. You can use the same timeouts for interactions with the database. We may want to have an option for a secrets manager, because if we're running microservice, it needs to have secrets, KMS adapter to it, sure. A throttling strategy, right? If we're not throttling services, they are unstable. And of course, a retry strategy, we can call it immediate retry. We can swap it out for something else later. Those are behaviors, and if we're passing behaviors, we need to be checking them with the options pattern. And finally, we have a choice for a backend and a logger. If we are writing something so sophisticated that require the options pattern, a logger is pretty much required. Yeah, right. We don't want to put loggers everywhere because they create side effects, but they're excellent for something this complicated, right? So, and then of course you can write an interface and satisfy it with a logger of your choice, and you can actually write the option in such a way that they are appended to a list. So we have now multi-directional logging. Suppose we're writing a Fargate containerized task launcher. I had to write one of those the other day. This is not easy. So Fargate is an API on top of Kubernetes, which is a nightmare to secure. So Fargate is a little bit easier in that regard. But still, we have to be vigilant, and we have to check the AWS config that it's correct, right? That it's not using static keys or anything like that. So we're using the configurator properly, that is getting its identity and its role from the EC2 instance where it's running on, not from an environmental variable. We can check for that. We want to provide a cluster name, so we have a single point of failure, a URL factory, sure. And then private subnet IDs and public subnet IDs. Well, see, Fargate does not differentiate subnets, public and private. It just has one place to put a subnet. It just asks for subnet IDs or a list of IDs. But that's a problem, because if we put a private service out on the public subnet, we could be leaking information or giving an attacker server-side request forgery type of vector, anything you can imagine. So we have to be really careful about that. And even if Fargate does not differentiate private and public subnets, we should. The same goes for security groups. Like in AWS, security group is like a firewall set of rules. It's very significant. So how can we differentiate? Well, we can, for example, when we get the subnet ID, we can check for that IP address and see if it starts with 10.0. That would indicate an intranet subnet. That's just an example. You can get more sophisticated than that. But the point being is that even if the API does not enforce public-private division, our implementation can, and our configuration checker can. We can check for that at initialization, and we should. Suppose we're writing hypothetical encrypted network tunnel. We want to specify a certain packet size, a key provider, yes, of course, a behavior, and we may want to have recovery fallback if our network tunnel is stateful. A journal fallback is great, sure, let's provide that, and of course validate it as we're leaning on that behavior. We'll need a nonce factory. That's always a complicated thing with encryption. Synchronizing nonces against across services at scale is very hard. And finally, we can even use an option called with error handler. Those are great. And this is an example, another one, where we can pass a closure as an option, and that is so convenient because sometimes we don't even care about every error. Like sometimes we want to set up an alert, or we're looking for a report on a particular error, and we can do that with an options pattern using the error handler, append it to a list of handlers, and rock on, right? That's a really flexible, great way of dealing with errors, and of course we can have a default one in there as well. That would make our service more secure. Error handling is a big part of security. So those are just examples of some things I got to work on and some things you can think of yourself. But here's an elephant in the room that I did not even bring up. Something I didn't even talk about this whole time that's so important. Just think back what are we doing with this, right? We're pulling that sophisticated logic, validation logic, into isolated closures, into functions that are localized, that each have to do with one area or two areas of concern and that are sensitive to each other, but are very limited in scope. We are setting up our options for easy unit testing. Here's the truth. There is no better initialization strategy for unit testing than the options pattern. And once you have a strong battery of unit tests that check for many different types of failure conditions, you add security and you make it in such a way that it's modular and flexible and extendable, right? You're not going to break any APIs if you add additional options, etc. It just makes it great. Tested code, thoroughly tested code is safe, and the option pattern gives you a hand by lending itself to easy automated testing. OWASP Top 10 2021, number 5 and number 4. Security misconfiguration, insecure design. This is a problem that should not be in top 10, right? We can solve this. We have the tools for it. We have the know-how. It requires a little bit of discipline, a little bit of a different mindset. This is coming from a functional paradigm. Functional programming paradigm is good. You can apply it, but most importantly, it can help you think and threat model and anticipate problems ahead of time. And if we use the options pattern, we can make a big chunk in this work that's required to resolve security misconfiguration and insecure design. Let's sum up. If something can be misused, it will be misused. Be secure by default. Weakened services should not even start. The options pattern guards against misconfiguration, invalid initialization states, and other vulnerabilities. The options pattern is convenient for automated testing. It is the best strategy, object initialization strategy for automated testing. And finally, implement the options pattern in your next major version release to bolster security with a boost of code readability, reliability, and resilience. This stuff really works. Use it. If you enjoyed this presentation, you can find a full compilable example at that QR code. I also want to bring to your attention a few resources. One of them is the classic presentation by Dave Cheney. This is one of the early discovery opportunities for me, how I learned the options pattern, and he explains even more all the great benefits of it. There's also a very detailed, good blog by Mark Sagi-Kazar that is excellent. And there's an interesting article about how this can be applied to database queries. Thank you so much for your attention. I enjoyed sharing the options pattern with you. I hope you learned something new, and keep in touch. Bye-bye.
Hi everyone, welcome to our talk, Assless Chaps. A novel combination of prior work to crack MS-CHAP and NTL MV1, or why MS-CHAP v2 doesn't cover its ass. I'm Michael Kruger, or underscore Cable Thief on Twitter. This is Dominic White, or Singe on Twitter. Today I'm going to be discussing, well, I'll be taking you through an MS-CHAP challenge response. I'll be taking you through why we can use hash lists rather than word lists for cracking these things, and also some ideas around that. Dominic is going to take over about halfway through, and he's going to take you through how he went in depth into the DES into the DES cryptography on the challenge response. He's going to talk about how he created a tool to do this a bit faster. And he's probably going to go down his optimizations and things that he took to get there. Anyway, switch over to these slides. Cool. So basically, the entire the entire industry has been carrying on using MSChap or NTLM-v1. So MSChap PEEP specifically because it's very, very convenient for Wi-Fi. You don't have to set up certificates, and well, you don't have to set up certificates for it to actually work, but you do need to set up certificates if you want it to be secure. But so industry, they keep using it. We hackers keep saying this is definitely dead. Industry keeps going, no, it's definitely alive. So to show you why it has problems and why we think it's technically dead, or it should be, put the last bullet in it, let's go through the MSChap exchange so you can get a better idea of what tool we created and then sort of what optimizations Dominic has implemented. So the MSChap challenge response. The idea behind it is to prove knowledge of a secret without transferring that secret over the wire. So to do that, we're going to go through this example using King Arthur and a Frenchman from Monty Python's Holy Grail. So the user or client will come along, give his username. The authenticator, in this instance would be the access point we're wanting to get onto, will provide a challenge. This challenge in the MSChap world is a 16-byte or 16-octet random string of bytes. At which point the Arthur will submit his own challenge to the Frenchman. This will be also 16 random bytes, and he will include an NT response. This NT response is created by taking the challenge that the Frenchman gave him, the challenge that he has, putting it together, and then taking the password that he has and encrypting that challenge so that it generates this random string of bytes. He will then submit it to the Frenchman. The Frenchman can then just inspect this. The Frenchman has the pure challenge. He can take this pure challenge, combine it with the challenge that he sent over, basically redo all the same operations, and if it matches the NT response, then he knows, okay, cool, Arthur has the same password I do, right? But MSChap is a synchronous authentication challenge response thing, whereby not only is Arthur authenticating to the Frenchman, it is the Frenchman also authenticating to Arthur. So the Frenchman, now that he has all this information, generates his own response, which is essentially all the same info about all the information that's transferred till now, as well as some bit of the password, which he will then send back to Arthur after having prepended an S equals for success. However, if he fails, Arthur gets sent a big fat F and gets told to bugger off. Cool. So let's dive into this a bit deeper. We have the challenge generation. Now, when I say challenge generation, I'm going to be talking about the challenge that is ultimately used in generating the NT response as well as the authenticator's response. So you'd think it was that 16 bytes that the Frenchman sent over. However, that is not the case. It is actually the username, the challenge provided by the Frenchman, and the challenge provided by Arthur. All these things are put together in a SHA, and then the first 8 bytes are taken from that, and that is used in the equation for future hashing. This is important to know because the way MSChap cracks is the same way that NTLM-v1 cracks. However, NTLM-v1 generates its challenge in a different way. So meanwhile, while both these things crack the same, they generate their challenges differently. Anyway, so from here on, the challenge is going to be this amalgamation of the 2 challenges as well as the username. Right? The thing that Arthur generates is he takes his password, he NT hashes it. NT hashing is basically just an MD4 sum. He then adds that to the challenge. Essentially, he encrypts the challenge using his NT hash. This generates the NT response, which is what he submits. So you can see he's encrypted the challenge with his NT hash. This gives the Frenchman the opportunity to encrypt the same challenge with the NT hash that he knows. And if it ends up in the same response, he knows that Arthur has the correct password. From the Frenchman side, he does some slightly different work because otherwise he could just submit Arthur's challenge back to Arthur. Sorry, Arthur's response back to Arthur, and Arthur we wouldn't really get the desired result. So what the Frenchman will do is he'll take the password, he'll MD4 it into an NT hash, he'll MD4 it again into an NT hash, in which case he'll add the username, he'll add some static magic that's in the RFC. So he'll sprinkle on a little bit of magic, he'll add in that same challenge, and then he will add in the NT response that Arthur provided him, and that is the response he submits. The SHA of all that is the response he submits to Arthur, if Arthur was successful in authenticating. Right? So if we look at this a bit closely, especially at the NT response generation, you'll notice that what actually goes into the final NT response is not necessarily the password. We can skip the password stage and just use the NT hash. It's the same from the other side with the Frenchman. We have the password, we convert it into an NT hash, and then we start using the NT hash. So once again, we can skip that step if we have the NT hash. So I was sitting there thinking about this, and I thought, well, if we only need the NT hash, and we have sources of NT hashes, such as Active Directory, or things like Have I Been Pwned, can't I use that and sort of pass the hash to get onto wireless networks? Given them passing the hash is essentially within the challenge response. All we have to do is skip the first step. So NT hash and then pass the hash. Right? So I went researching. HostAPD and WPA supplicant both support this. You can see in these example configs I've provided, the main difference is you just prepend hash and colon, and then you give it the hash in both cases. So in the supplicant case, your password equals hash, colon, and then in the EAP user file case for HostAPD at the bottom, it's a case of where you would usually put the password. You just say hash, colon. So now we can use hash lists instead of word lists. Current MS chat modes take very long. There's a lot of wasted NT hashes if you only use cracked ones, and there are places you can go to get NT hashes. So the idea behind this was, why bother cracking when we can get like word lists of actual passwords from somewhere and then just use them and pass the hash? And what really intrigued me was Troy Hunt from Have I Been Pwned providing NT hashes, right? This means we have a really large database of real world passwords that it's possible people have chosen as their Active Directory passwords. And should we capture an MS Chat challenge response, we can use that as a word list to quickly check whether this person has reused a password. So I thought it would be very convenient. So I went looking on how I would go about cracking NT MS Chat v2 using an NT hash. And I found the Hashcat forums in 2016, two forum posts where they break the challenge response into multiple NT hash segments, into multiple DES sections, and then they crack the DES section. So reading through these two forum posts, what they do is they basically, given that the DES key is only 8 bytes long, they go through it and crack the entire DES key space to get back the NT hash. So I thought, okay, cool. We don't even need to use hash lists. We have a way of guaranteed getting back the user's NT hash. So I promptly put that into my little MacBook pressed enter to brute force the entire key space. It said something like 4 years or something like that. So I went back to my idea of using hash lists. So I tried going through the whole rigmarole of setting up this multi-phase DES cracking, where I split up my NT hashes into little sections and trying using those. However, this became a mission. So I thought, why not create new Hashcat modes? How difficult can it be? Essentially, all I'm going to be doing is taking mode 5500 and taking out one MD4, right? And then it basically is perfect, right? So last SenseCon, which is a internal hackathon, I got a team together and we built these new hash modes. So we built 27,000 and 27,100, one for NetNTL MV1, which can apply to MSChap, and then one for NetNTL MV2. It wasn't as easy as I thought it would be with just removing one MD4 sum, but it now works and it should be in Hashcat. So now we have a way to provide just a long list of hashes, so a hash list rather than a word list, and then that gets us, we can crack NT hashes, sorry, NetNTL MV1 hashes with hash lists. So we can use Troy Hunt's Have I Been Pawned database. Right, so let me just demo this to you. I have created my fancy new hash mode. We're going to use the example hash provided by Hashcat, now that's there. And we should see that we crack successfully using an NT hash. And you'll notice at the end, B4, B9, that is a NTLM hash for the word Hashcat. Right, so brilliant. So now, considering that I've taken away an operation, there should be a big speed increase, right? So I was all excited. We can see that my hash gets me 6,000 kilohashes a second. If we compare that to the old mode that has an entire operation more, we get 220 mega hashes, which is a lot faster, right? So why is this the case? Well, after some questions to the Hashcat people, Hashcat has the concept of amplifiers. So with the normal mode, we are essentially transferring over a word and then potentially applying a big bunch of rules to it, at which point that word now on the GPU blows up into a few thousand different words, right? If we think about what we're doing with my hash mode, we are taking a hash, transferring it to the GPU, checking it, and then we can't do any additional modifiers to it. So we throw it away and we go to the next hash and the next hash. So what happens is we get throttled by the bus to the GPU a lot more. And this adds a hell of a lot of overhead and makes it infinitely slower. So to get around this, Dominic is going to take over from this point forward. Right, so let me pass this over to Dominic now, and he can talk about his new approach of how he sort of optimized and got around those optimization problems that I had. Right, over to you, Dominic.
Thanks, Michael. Hello, everyone. Okay, so Michael did all the hard work and talked a lot about arses. I'm going to do the easy work and talk more about asses. So, what Michael showed you in the exchange is that at some point you've got this password hash, which is turned into an NT response. And the way that's done in a little more detail is we take the password hash and we split it up into 3 keys. And then each of those keys is used with the challenge separately in a separate cryptographic operation. So it's not like triple DES where it's 3 DES rounds. These are literally 3 separate single DES rounds. The other thing that's interesting here is because there isn't enough bytes in the password hash and a DES key is 7 bytes long, for the last key, they end up padding it with 5 bytes. So when each of those things are encrypted, we produce the NT NT response. Now, when we're cracking this, we're going the other way around. We've got the challenge and we've got the NT response, and we're trying to get the password hash. And we know that there's these 3 DES operations. So we need to figure out these 3 keys. We've got the challenge and we've got the ciphertext that gets generated. So we're going to go in reverse. Now, the thing that pops out as kind of the most obvious is this key 3, which has these 2 bytes that are padded. And what we can do with those is we can brute force them, because the key space for that is 65,535 only. DES operations are pretty efficient on modern hardware. That's not a lot of DES operations. And that's the maximum key space. So average time, you're going to find that in half that. So we can brute force those 2 bytes, and then we'll get the last 2 bytes of the password hash. And then we just need to recover the other 2 keys at this point. Now, that's not a new observation. This is a slide from Joshua Wright's deck at DEF CON 11 at Alexis Park in 2003. And you can see in the middle of the slide there, he's got weak DES key selection, permits recovery of 2 bytes of the NT hash. So we've known this for a long time. And later on, when Moxie Marlinspike and David Hulton at DC20 in 2012 presented their work, they used this, but they took it one step further, another optimization. And that was, instead of going through the DES key space twice, brute forcing the 2 keys, they go through the DES key space once, because they do 1 cryptographic operation and 2 compare operations. So we're looking for this key, these 2 different keys, so we can perform this cryptographic operation and then go, does it match either of the keys? So that was another optimization they came up with in 2012. And if we look at the history of the speed here, so the other work that Moxie and David Hulton did was they introduced FPGAs, but it's useful to understand the history to understand the future. So in 1998, the EFF produced these custom chips, ASICs, and at an exorbitant cost of $250,000. And that could brute force all of the DES key space within 227 hours. And you can see the keys per second on the right there. Now, what's interesting is if you look going forward from 1998 to 2020, there isn't massive jumps in the number of keys per second. Well, there is a big jump between 2006 and 2012. But then after that, it actually goes backwards before we go forwards. What there is a big change in is price between 1998 and 2006. So the $250,000 to $10,000 is a big difference. And that was because FPGAs allow us to effectively create custom programmable chip pathways without needing to design custom chips. And so in 2006, the Copacabana team did that with an FPGA. It actually took longer, but at only $10,000, big improvement. Then what Moxie and Dave did in 2012 was they also used FPGAs, but with their optimizations, they were able to reduce the time down to 23 hours, as well as a dramatic speed improvement using their FPGA approach. And they built Cloudcracker, if some of you remember that. But then by 2016, Hashcat was starting to catch up here. So here I've used 32 RTX 980s as an example with what they would have cost at the time and that speed. And the reason I've used 32 of them is because that gives us a comparable cost to the 2006 Copacabana team. And so, of course, you could use more or less. And then in 2020, using some of Chicken Man's stats for the GTX 3080s, we're still sitting around 10,000, well, actually 11,000, but we've now managed to get to speeds that the FPGAs were doing in 2012. What you should take from all of this, though, is it's slow. It all requires DES brute forcing, and it's slow. So what that means is you're guaranteed to get a response, but it's not necessarily well optimized. So we can improve on that pretty dramatically with ASLIS, and that's what we did. So MS-CHAP version 2 and NTLM version 1 doesn't protect its ass because you've got these 2 bytes that you can brute force really easily. Now, this is known, it's been used by others. In Hashcat, for example, it does an early discard that if the last 2 bytes don't match of the hash, it doesn't send them through. What I did is something different, and it's really nothing more interesting than reducing the hash list up front by looking for the two bytes. So here's an example, grep saying, show me all the NT hashes from an NT hash list, like the have I been pwned list that Michael spoke about, that match those last 2 bytes. So if we take the Hashcat example, instead of doing an early discard in Hashcat's code, what I'm doing is just sending a reduced list to Hashcat in the first place. And when I did that as an initial POC, what I saw is that Hashcat was running around 8 seconds, and my crappy POC was under a second. So there's 2 sample hashes with 2 word lists, a small word list and the have I been pwned word list. And we were going from 2.5 minutes, well, actually nearly 3 minutes, sorry, to 46 seconds, or a minute to 41 seconds, or 10 seconds to under a second. Now that's not amazing, but it's enough to tingle my spidey senses and tell me there's something there. So like Sir Robin, I bravely went forth and traveled down this dark path. And this dark path is the dark path of performance optimization. If any of you have ever gotten stuck in this, it can be quite rewarding, but there's a lot of misleading pathways it can take you down. So the first thing is I did quite simplistically is instead of using grep, I used ripgrep. Any of you familiar with ripgrep? It's quite a lot faster for big files than normal grep written in Rust, and it's got a bunch of other optimizations. That got me a bunch of extra speed. And then I simplistically started operating on the hashes that were returned from ripgrep as they were returned, rather than waiting for the whole command to finish before working on them. Things like that started giving me a bit of a speed up. And more importantly, I started building a Python POC. I then worked out that there were 2 sets of optimizations we could do on the lookup of the last 2 bytes. So instead of brute forcing through the key space of 65,535, I did a frequency analysis and noticed that some sets of 2 bytes were more common than others in an otherwise randomized set. Outside of that, some passwords are more common than others. So something like password 1 is going to be more common than a password manager generated password. And the last 2 bytes in password 1 then within a frequency set go up. So using a combination of a frequency sorted list, so where I didn't unique the passwords, as well as a bunch of 2 bytes, it gave me a pretty decent lookup. That's actually in the GitHub repository for this if you want it. I later removed this, so that gave me a pretty decent speed up with Python and the DES operations. It didn't give me a speed up use when I eventually moved to what I'll get to in a bit. Then I started doing a bunch of file tricks. So can I seek from different places in the file? Can I reduce the file size so that I've got less to seek through? And what I realized was I was actually just doing the same kind of stuff databases already do, just really badly. So at that point, I moved to a database. I first tried MariaDB, and it was much slower. I then tried SQLite, and it was even slower. But I sort of scratched my head at this because databases should be able to handle millions of lines quite easily, until a developer friend pointed out that actually indexes are the things that make databases fast, not just using a database. So putting indexes on my hash lookups managed to improve things quite dramatically. So you can imagine I'm searching for hashes that have these 2 bytes, so I can index the 2 bytes that are put into a database, and that gives me pretty efficient lookup. It uses binary trees, balanced trees, which gives you in big O notation log n performance, which is important for in a moment. And then I built it in Rust. Rust obviously being compiled, it's faster than Python or janky bash script. And Rust also just sort of encourages good programming habits that make your stuff go a bit faster. I then tried a bunch of threading things, which have been quite misleading. For the most part, they either gave me the same performance as not using them, or worse performance, or in some cases, very slight performance improvements. So I'm actually only using threading at this point for the 2 bytes lookup with a couple of threads, which gives me a slight speed optimization on average. But threading wasn't more efficient, which is very different from the FPGA type stuff. And it's really just because so few operations are happening. So let's get into things that look like I know what I'm talking about. So if we were to map the performance, the comparative performance of the DES brute force, so going through the key space of DES, versus the approach we're taking in Atlas. So in Atlas, we do the lookup, which is a B-tree lookup. And then for the returned hashes, we need to crack the remaining keys. So there are some DES operations. Now, if we assume the lookup and the DES operations are the same, we can kind of plot some big O notation on a graph. So I've got two axes there. The y-axis is the number of operations, and the x-axis is the number of hashes. So how many hashes do we get per number of operations? Both of those scales are logarithmic scales. So a straight line is actually a curve, a logarithmic curve. And what you'll see at some point, they cross over. So the blue line is DES brute force, and the red line is the ASLIS approach. And the point at which they cross over for worst case performance is about 4.3 billion hashes. So what that means is if you have an ASLIS database that has 4.3 billion hashes in it, then a DES operation, and assuming worst case performance, so the hash isn't is at the end and you have to look up everything, then a DES brute force would be the same. For the median case, that turns into 17 billion hashes. So that's pretty big. So if you think about the have I been pwned list, that's about 600 million hashes. So 17 billion or even 4.3 billion for the worst case is pretty significant. But if you're going bigger than that, it's worth recognizing that DES is going to be, a DES brute force is going to be better. Plus, a DES brute force is guaranteed to give you a hash. So for computer hashes or non-readable hashes, that's a better approach. But if you're looking for human readable hashes, the kind of things a user's actually chosen, then ASLIS is going to have an obvious advantage because it's going to favor those over a random walk through DES key space. All right, so this is the money shot here on my now old laptop. I need to rerun the benchmarks on the Mac M1 using 3 different hashes. So hash 3 was not present in any of those word lists. And then there's 3 word lists: a small private word list, the RockU database, obviously, and then the Have I Been Pwned database. So the bottom right shows worst case performance. So that's a hash that wasn't found, so we effectively had to go through all of the Have I Been Pwned database to get there. And you can see worst case performance was sitting at 63 milliseconds. Best case performance was sitting at 11 milliseconds, and the median case is sort of 15, 19. I've got it written down there, 13 milliseconds. I should read my own slides. Now, if you think about the Rip Van Winkle slide and you think about how we were measuring the performance in hours, this is a massive improvement at the cost of not getting a guaranteed result. So the hash has to be in your hash database. But if you're doing a really quick look, that gives you an immediate result that at least tells you, okay, now it's worthwhile to engage in a DES key space brute force, then great. All right, so this is available right now on our GitHub, github.com/sensepost/aslis-chaps. And I'm going to give you a quick demo on that. Okay, so now we've switched over to the demo. And the first thing we need is a word list, or more importantly, a hash list. So if we look at RockU, we've got clear text passwords. So we're going to need to convert that into the ASLIS database format. It's a SQLite database. I've already created one here. If you look inside of it, what it has are empty hashes split up into the 3 key components. So here I'm just looking at the top 5 from here. A little bit later, I'll show you how to generate this hash list. Okay, so now that we've got our database, what we need is a hash. So if we look here, I've got an examples hash we've captured from a user called Sally. It's got the NT response and it's got the challenge. We look at ASLIS chaps, we give it the challenge, then we give it the response, and then we give it the database. So here we're using rocku.db. When we run it, we get our response very quickly. If we run it with time, you can see it took 0.015 seconds in total, which is pretty cool. Okay, now if we were to compare it with Hashcat's 5500 mode, which gives us the clear text using a clear text password list, I'm using the same hash, and I'm going to make it quiet, disable the pot file. Then I'm using some Apple Silicon. I need to say D2. When I run it, I'm able to get the password. If we now run that with a timer, you can see that takes 1.166 seconds in total. So that's 100 times speed difference almost between the two. Okay, so switching back to the slides from our demo, the next optimization we wanted to talk about is when you're looking at the Have I Been Pwned list, you've got a lot of passwords in there that typically aren't chosen by corporate Active Directory domain users. And when you're cracking an MS-CHAP hash from a Wi-Fi exchange, that's probably from a Microsoft Active Directory controlled Wi-Fi network, which means the user is going to be using something that needs an uppercase, a lowercase, and a number in it, like the password one is capital P. But Have I Been Pwned has got things like 1, 2, 3, 4, 5, 6, and Michael all lowercase, stupid name if you ask me. And those sorts of things. Here's some stats from the NSC CSC. Yeah, get some late night dyslexia here about what's in there. So this is not a great hash list for corporate passwords. What is a good hash list, produces good hash lists, is Hashcat's rules-based attacks. So I thought it would be really nice if we could use Hashcat's rule-based attacks to generate assless databases. So this is what Hashcat does with an overly simplistic view of what Hashcat does with rules. If you take a password list that has password and the company name in it, and it's got 3 simple rules of adding numbers, adding dates, and changing the case, then you can get the kind of clear text examples you get on the right. So I built some Hashcat, very simple modification to one of the Hashcat kernels to effectively generate CSV files for you that have the hashes in, that can then be consumed by the database creation utility in Atlas, as well as you can then use the normal Hashcat functionality to pass rules. So I'm going to give you a quick demo of that. This is all available on the GitHub repository. Okay, so we're going to give you the demo of generating hash lists. If we look at our RockU clear text database, we've got clear text passwords in there. We need to turn that into a hash list. So there's 2 ways we can do that. The one is to convert it directly into a hash list using a Python program that's included within Atlas, and that's what I'm going to show you first. And then the second is to expand it using the rules from Hashcat. Okay, so NT-hash from clear just takes the database and spits out hashes. So I'm not going to do all of them. I'm just going to do the head. And you can see it puts it in this special format with the last 2 bytes in the beginning, and then the first 7 bytes, and then the second 7 bytes. So that is the format the CSV file needs to be in to be imported into the SQLite database. All right, next I'll show you how you can use Hashcat. And the reason I'd want to use Hashcat to do this is because then I can get rules to increase the number of passwords that are generated. I'm giving it an impossible to crack hash so that it doesn't match the hash and then exit early. And I've applied the modifications from the Atlas repository on the 1000 mode. So you can see -r is the rule file for the best64 rule, which just comes with Hashcat. You can use whatever rule you like. And then we can output that to the CSV file. It can take some time. So instead, I'm just going to use the CSV file we generated before for the purposes of this demo. If you look at it, there's our hashes. It's the full RockU. That's just the top of it. So there's another file included in the Atlas repository called make SQLite DB. You give it the name of the database you want to create. You give it the CSV file. It'll first import all of those into the SQLite database. After it's finished importing them, it will create the index on it. For something like RockU, that can take a couple of minutes. For something like Have I Been Pwned, that can take tens of minutes. So it depends on the size of thing, but it's a once-off cost. Once you've got it, you're done. And then the database with the index increases the size by about 63%. So the RockU DB is about 63% bigger than RockU.txt, which is worth bearing in mind, but it's really not massive hash requirements at this point. So there's one more thing that I want to show you, which is if you've got an NTLM SSP or NTLM ESS hash. Here's an example of one taken from the Hashcat example hashes. And what you'll see is when I put what looks like the challenge and response into Atlas, it just hangs. I haven't managed to track down this bug yet. But if you ever have Atlas just hanging like this, it means you've got an SSP hash. So EvilMog has some scripts to fix that up. I found them quite complicated, so I've just written something very simple. It's called NTLM SSP. And you give it the LM part, and you give it the challenge part from the SSP hash. It'll spit out the server challenge, which is what you can then use as the challenge to pass to Atlas. So it's a small conversion step that you need to do for NTLM version 1 ESS or SSP hashes. I'm not going to go into all of the specifics there, but it's worthwhile noting if you're dealing with NTLM version 1. So you can see I first tried it with RockU, it wasn't in there, so then I tried it with Have I Been Pwned. Okay, so that was demoing the hash list creation, and that's how you can create your own databases for use with Atlas. That brings me to the end of my section, and just a quick recap, really what I was showing is how, because MS-CHAP and NTLM version 1 don't protect their ass, that you can do this easy brute force of the last 2 bytes. You can use that to reduce the number of hashes you look at in the first place. And the way you can very efficiently reduce those number of hashes is using a database lookup with some compiled code. And doing that has produced a utility which improves the state of the art with this cracking. It's important to mention that this also works for NTLM version 1 or NTLM version 1 SSP. There's a utility in the GitHub repository if you want to convert an SSP hash. So if you've got an NTLM version 1 hash, like something from Petipotum maybe, I still need to look into that, then you might be able to recover it quite quickly using assless. And on that note, I'm going to hand back to Michael.
Cool. Thank you, Dominic. All right. So just to recap everything. Why are we doing this? We want to recover NT hashes quickly. As I showed you, with an NT hash, you can pass the hash. We can then pass the hash to connect to Wi-Fi. We can pass the hash to connect to VPNs. You can pass the hash on normal Windows networks as well. The last one is also to host access points that hopefully you can trick people into connecting to you so that you can do sort of person in the middle attacks and attack them further, as it were. Okay, so in summary, MS-CHAP v2 used the NT hash, not the clear text password. You can use full NT hash lists, including the uncracked ones. New hashcat modes we created with 27,100 for NTLM v1 and NTLM v2. NTLM v1, of course, being the same way you crack MS-CHAP. MS-CHAP exposes his ass, easy brute of the last 2 bytes. These can reduce the hash list to crack against, so it makes it very, very quick. Index DB lookups cost less than DES brute forces, at less than 17 billion hashes on the average case. So, people to thank. My hackathon team from Orange Cyber Defense. This is the people who helped me create the initial proof of concept for the Hashcat module. Once I had the Hashcat module in a pull request, Atom and Chicken Man gave me a lot of help making it an actual good Hashcat module. We then want to thank Joshua Wright for Asleep. Basically, all work is built off the shoulders of giants sort of thing. Moxie and David for CloudCrack. And then if you are interested in this sort of technique of cracking hashes but skipping some steps in the front, Chicken Man did a talk at DEF CON for hash shucking, which is the name of this technique. And then once again, you can get the assless chaps from the repo listed. The end. And cool, thank you.
Well, so this is Vignesh presenting up at 0xCon with respect to attack and defense techniques with Kubernetes. So about myself, I've been in this information security field for like 8+ years. I've been based out of Tamil Nadu, a small state in India. And apart from that, I can say like my key achievements, I've been into global top 10 the Hack the Box, and some various conferences I've been speaker like Balkan with where I spoke like for Active Directory security, and for ThreatCon where I spoke like body area networks, and I also other areas of interest were like APT, threat intelligence, and advisory emulation. So this is all in short about me. So what's agenda for today is how we can attack and defend up the Kubernetes attacks and clusters, or in short pods, and how we can relate it up with Mitre attacks. And I'll be showing up some attack scenarios, and I'll be sharing you some cheat sheet kind of series for defense mechanisms, and I'll be explaining up how it will be helpful with respect to this securing the environment. So the key idea of this presentation is to harden your environment and to highlight some of the common attack scenarios which I have faced during the times of research. So let's jump into the introduction of K8. So basically K8 alias Kubernetes is like an workload and containerized workload and services platform where you can manage up the workloads for multiple instances, and where also you can automate it up. It's from Google, that all guys knows about it. So, and the right side you can see visualize some of the pods, kubelets, Docker. So this is when a developer pushes something, it will be pushed into kubelet, and that kubelet will be executing through controller and scheduler. So this is how the basic Kubernetes cluster works. So if someone is unaware about before the talk, I assume that all were aware about pods, containers, kubelets, etc. And what is Mitre is like a similar technique or a framework where the people will use to derive a threat model, and as an attacker or a red teamer you can use it for red teaming emulation based activities and some adversary simulation activities as well. So here with respect to K8 clusters, I derive into similar to the path of cyber kill chain. So cyber kill chain similar process like initial reconnaissance, execution, vulnerability analysis, exploitation, persistence, etc. But with respect to K8 cluster, there will be an initial access through some cloud credentials, and there will be some malicious execution which will be performed at the container, and it will be persistence inside the backdoor container, and the privileges will be escalated, and from there the defense evasion like by clearing logs, etc. And if you have the credential access, you can dump it from the K8 secrets or whatever the configuration files available in the pods. And if you have some cloud resources, you can write and filter out the endpoint. And the maximum impact which you can cause were data destruction, resource hijacking, and you can cause DDoS attacks as well. And with respect to defense matrix, as a first rule of thumb, prevention is better than cure. So basically you need to harden the cluster. I'll be sharing a few points from my research with respect to K8 clusters. So hardening, credential hardening, application hardening, platform hardening, and with respect to detection, how far you can analyze the network inbound and outbound traffic, and platform monitoring, runtime analysis, if there is any user behavior analysis, and you can isolate based on the detection mechanism, and you can evade the threat. So this is in short all about for K8 clusters. And some of the open source tools which are available for K8 defense specifically were Falcon, Trivy, and Statboard, which you can use it for statistics. And whatever the examples which I shown here were set it up using Falcon with Slack. So let me go ahead. Before that, I'll be showing you up some attack tools like Kubesploit, Cube Hunter. It's like a benchmarking tool, and Pirates, which you can use it for emulation. So if you want to set up the parallel setup in your environment, you can use KubeGoat, which is like a similar vulnerable pod where you can compromise and see. And secondly, you can use Falcon for runtime monitoring, and for alerting you can use some channels like Slack or something like Telegram bots in order to alert you up, or you can configure some SMTP server with mail as well. So whenever defending the ports, there were some common challenges persist. First of all, we should be clear before handing up what were the challenges. So first challenge when it comes to place is pods and containers will be in communication, and whenever there is a high usability, there will be in less security. With respect to K, there is more options to configure. And with respect to multi-user tenants, there is an always chance of compromise, since we always will be focusing on handing off core tenant and we'll be leaving out other tenants. And moreover, all the runtime monitoring would be completely dependent on the logging perspective. If logging is compromised, everything is compromised. Or if there is some failure in alerts or something like that, it will be completely compromised. So with respect to K clusters, some of the common attack scenarios where once you compromise, as I showed in Meter earlier, you can use it for like an C2 server pod, you can use it like that, or you can use it for some crypto mining, which is a common mechanism. You can also scan some pods online if it is available, and you can see some crypto mining malware is running up. And some internal network mapping or network discovery can also be carried out, and privilege escalation also can be carried out. And credential dumping is under research, where you can credential dump the credentials as well. And you can also execute some rootkits, and you can place some execution on process whichever running on temp. And you can also use it for pivoting as well. So when it comes to securing up, it can be categorized into 4 parts. First part is how you can harden the host. Second part is how you can harden the components, and how you can harden the components at building or deploying and runtime phases. So in short, it would be like an entire network setup, and where we can harden it up. So here there is a basic structure which I have put it up. So here you can see some Kubernetes control manager, cloud control manager, and there will be a Kubernetes API server. And from there it will be the traffic will be inverted into some certain kubelets or Kubernetes nodes, and that would be focusing on etcd and other stuff. So this is an in short network diagram or some architecture which I am going to explain to you. So some basics were like kubelet, which runs on each node of the cluster. It makes sure that all the containers were maintaining the uptime on your pod. Kubeproxy is like a network proxy server which will be running on each cluster, where it will be used for in-house communication or internal communication between the pods, and some container runtime which is responsible for managing and executing the containers. So before securing part, I would like to explain some of the nodes which you need to keep an eye on. So whenever there is an Kubernetes master node is running up, there will be 3 ports which you need to configure on, which you can alter it up based on your internal configuration. So the ports would be like Kubelet API, read-only Kubelet API, node port services, which will be running by default on the master nodes. And if there is an SSH access, you need to limit the access by assigning some host resources, and also you need to ask users to use kubectl execute to provide direct access to the host. If possible, you can use some Kubernetes authorization plugins where you can write some namespaces or containers in order to restrict access to that core node of the kubelet. And with respective to the work node, you can write some SKU policy and you can monitor in Kubernetes work nodes like 6443 where the core API server will be running, and there will be a scheduler and controller manager running at 10251 and 252, and there will be an always read-only kubelet API running at 10255. So whenever you are implementing some of the core network mechanisms, you should be focusing on these ports, which will help you to monitor up and evade controls. So some other key points for attackers and defenders as well. So whenever there is an API request, you should be controlling what API request is coming up. You should be it's completely dependent on the API request, and that API request can be classified and can be authenticated as well. So whenever you are using some small clusters, you can use turn on the service account tokens for authentication, or if you are using some large clusters, you can use like OpenID Connect, or you can use some short-lived tokens which are like key-based tokens. So assume like there is a web request which is coming between server and client, you can assume like the communication should be smooth enough by validating the key-based authentication, or you can use some centralized groups, and you can also use some managed distributions like GKE, EKS and AKS support authentication, where it will be provided by the IAM providers. And also one more point which you can remember is like you can use Kubernetes impersonation, where you can use it for managing cloud clusters and on-prem clusters in order to having access to API server configuration. You can just monitor using the Kubernetes impersonation services. And for authorization, you can also use an RBAC server, which is a role-based method, where you can give how much you need to access and what authorization needs to be made. It's similar to the access control of the application. And also you might need to restrict the access to the etcd service as well, which is a core of the kubelet pod. So when it comes to dashboard here I refer like what were the key mechanisms, or whenever it is highlighting. So dashboard is an area where an attacker would be more concentrating or relying upon, where he can collect maximum statistics. So whenever it comes to the dashboard, you should not expose it to the public, and you should be always having the authentication, and please keep it within your LAN, and always turn on RBAC if possible. Some dashboard access should be limited with some LDAP access, and always remember one point, like the service account of your Active Directory should be differing from the kubelet account, and you should not grant the service account for dashboard's highest privileges. And also please remember that whenever you are configuring the network policies, it should block from pod to dashboard. It should be blocking up the internal pods, and you should also, if you are running pods like before 1.8, you should be also be aware of the fact like the dashboard will be running with full privileges if before 1.8, where the role binding is only with cluster admin. You can also use authenticate using some reverse proxy, or you can embed using Kubernetes impersonation by embedding tokens, which you can use it for privileging the service account as well as managing service accounts as well, cloud accounts as well. So this part is corely related to some dashboard part. So if I summarize up to now, what I have explained is there will be, assuming there will be some master node and work node, and which will be alerted through some dashboard. So these are some key points which you need to focus on whenever you are protecting up. And other key line of defense which I want to highlight it is like you can use it like in cheat sheet. You should always use the authorized images, and if possible run distroless images destroyless images, in the sense you can limit the kernel activities and other activities with respective to the containers, and use container registry and image scanner, so you can keep up to date with respective to the vulnerabilities which are in public. And you can also use namespaces to isolate one resource from another resources. And when you can also use Kubernetes security policy, but always remember like some key points. You should never run the application process as root. Also, do not allow privilege escalation. Use always in root only file system. And you should also use SE Linux options if it is available. And please remember that whenever you are configuring your own application, you should be using your own Kubernetes service account. And never ever mount the service account credentials with respect to some container. If you are mounting up for compliance purposes, it should not be accessing up the Kubernetes API. Make sure it's not accessing the Kubernetes API. So with respective to RBAC controls, you can implement role-based access controls as well. If in addition to that, you can implement service-based authorization, and you can also implement some network policies, which I have showed it up over here. So here I have just wrote a sample YAML file, which will be monitoring, selecting up the pod which is running on port 80, and always encrypt the secrets at rest. And when it comes to runtime activity, make sure you are monitoring all the process activities, and whatever the network communication happening between the external clients and servers with respect to the containerized services, you should be always monitoring up. And whichever running with respect to privileged flag like cap drop and cap add, you can set it up and monitor it up. And you also try to make sure that proper isolation is made between Docker containers and underlying host. Also, you make sure that you need to restrict the usage with respect to file systems. Also, make sure read-only root file system has been implemented. And whenever rejection of containers with root privileges or restriction of containers with respect to privilege principles, it should be also be taken care. So these are like runtime key activities which you need to monitor up whenever there is an alert or something, or which you need to figure it out. And with respect to sandboxing, you can use things like Kata containers, where you can isolate containers, and you can use gvisor, which you can use to host to kernel, and you can use Firecracker, which you can use with respect to seg groups and user space and namespace. And you need to enable some audit logging. I have showed you how the normal sample audit logging here. You can see what kind of event which needs to be done, and what is the timestamp, what is the audit ID, what is the stage, and which namespace, which username, and it should also include source and requested timespace as well. So this is a sample audit logging which you can keep it up for sandboxing as well. So if you ask me to summarize up what were the key things which were happened till now is, I have explained you what is Keynode, what is the K8 cluster, how the master node and work node has been to be monitored, and what were the key mechanisms which you can use to secure up runtime, and as well as with respect to dashboard and host network, and with respect to audit logging as well. So if you want to set it up and play around with respect to your end as well, you can use some threat monitoring platform with some mini K8 bots like Minikube, and you can also use continuous monitoring like Falcon, and you can also map the tickets with your SOC tools like Splunk, etc. So now with respective to attack and defense scenarios, I'll be showing up some 1 or 2 scenarios where you can focus on it for alerts, how it will be alerted up. So here I have run an Monero miner inside a K8 cluster, and here you can see the namespaces which is running on my machine. Once the namespace is executed, the attackers will execute common commands. We'll be following up the meter techniques. Here I have executed some common commands like IDs, and I try to run in some Nginx shell, and I try to execute some of the pods and some of the reconnaissance data as well. So here are some snapshot alerts from command line. Here you can see I have tried to write an file into Nginx root, and this is the alert with respective to alert. Here whatever I used is shell demo, where you can use it for alerting mechanisms, and I have just fired up the shell. You can see what's the command line I have executed, and what's the pod name, and what's the procedure it has been triggered up. And another thing you might ask, like, what if I change the namespace, or what if I used to mount the namespace? So using the previous define mechanism, I have wrote an alert. So here you can see, using Falcon, you can see whenever there is a mounting related to changing in thread space, or mounting related to bin bash points, you can get alerts as well. And another alert is, if I suppose, as I said, the key mechanism for runtime security is logs. If I delete the logs, you can also monitor it up. You can, so basically whatever it's logging at the journalctl or with respective to system alerts, everything would be alerted over here, and it will be logged up over here. So this is all in short related to my presentation. So I hope you enjoyed the presentation with respective to that. And for further reads, you can always go with respective to awesome K8 security, where you have multiple K8 security papers. I hope this presentation also will get added over there, and Microsoft MetaMatrix as well. And you can, for beginners, you can set up with Falcon and other setup. So that's it from my side. I hope you have a wonderful day ahead. Thank you.
Hi, my name is Keith McCunn, and my talk is titled Beyond String Theory, Symbolically Enhanced Reverse Engineering. So let's get to it. The agenda, who am I? I'm going to talk about why you should listen to me, what I've done. I'm going to talk about binary reverse engineering, some of the hard problems that exist, why it's challenging to actually just to walk through some binaries, what can make it really grueling process. We're going to talk about symbolic execution, and we can talk about what anger is and how it can facilitate this, to walk through some of the basic steps in setting up a session. And then we can talk about some of the power that it has to help you find bugs, explore program paths autonomously, and actually automate some reverse engineering processes. And I got to talk about the hard problems before I get to anger, so you're aware of that. And then we'll cover some applications that other folks came up with, just quickly run through some of the cool things people have done, contemporary research. And at the end, if you want to ask questions, you can contact me. So who am I? I'm a security researcher. My name's Keith, as I mentioned. I do penetration testing. I do vulnerability assessment, source code review. It's my favorite. Reverse engineering is my favorite. So if you have code you need me to read for secure analysis, you want to know if there's any bugs that people can use to break it, or secure standards it's not adhering to, contact me. I've got a company set up to handle this kind of stuff. I also wrote 2 books. One of them is called the Android Security Cookbook, which I released in 2012. It has, it's a collection of recipes that you can use to break open an Android app, reverse engineer it, and assess it for vulnerabilities. And the other book I wrote is called The Penetration Testing with a Bash Shell, and it's basically also a collection of small recipes that make it easier to use Bash for automating penetration testing tasks. And currently I'm working on my master's, which focuses on symbolic execution for race condition detection. So I'm going to use a symbolic execution engine to autonomously find race conditions in binaries. Some quick terminology. Reverse engineering, I'm going to throw that word around a lot. It's basically the process of unpacking a program to detail its behavior. Here we're focused on binary programs. Okay, and if you're unpacking a program's behavior, you're going to have a lot of this word thrown around. A block of a program. A block is just a contiguous section of instructions separated by jumps and calls. Conditional separations of stuff. You want to know which blocks follow which. And if you're going to do that, you want to know the precedence of blocks. You're going to have to derive a control flow graph. And this is a directed graph that shows you which block will follow which and how they'll branch and split off into one another. Very important if you're doing reverse engineering. And again, we're going to talk about symbolic execution. And symbolic execution is all about the association of symbolic states. And a state is basically a hazy collection of instructions which loosely represents a block. It's associated to a set of metadata, which is vector register memory values. So you can make sense of what will happen when you reach the state in the program. A block doesn't have that, so this is why I'm saying a state is this association of metadata. So the typical process with reverse engineering. You typically load up your binary if it's loadable. You might have ALF sections or things that are broken. Program load statements that are all messed up in the wrong place. But you load it up in binary, the binary in Binary Ninja, either Pro, Hopper, Hydra, Redaria, what have you. There's a suite of tools now that make this very easy. You would then typically check the strings, try to disassemble stuff, do cross-referencing of function calls and variable references. You try, hope that there isn't a lot of obfuscation that makes this hard. In terms of like complex CFGs, obfuscated function names, etc. And you hope. That's kind of the general approach. But so this is the typical process. But what makes this hard? Number one thing that makes it difficult is complex CFGs. So if you're trying to in your head derive what will happen in a CFG, these are the kind of hard edges to the problem. You could have nested loops, and if you don't know what this is, like I just took a snapshot of a binary I was looking at, and these blue lines, they're all individual ways to enter a loop. So if you're reading this by hand, you can understand this is going to be extremely grueling, making sense of how this loop actually behaves in summation. The other thing that makes it very difficult is complex pointer arithmetic. So you might have these references to memory based on registers that are, summing and multiplying and scaling, indexing and basing, based on registers that take a long time to work out where exactly in memory this is trying to point. And here we even have like a complex pointer arithmetic for a comparison to break up a block. You might also have data-dependent branching and calling, and here is an example from a CTF, but it's not so uncommon to happen in actual real-world binaries. What this does is fgets it calls fgets, which reads a string from a file descriptor. The file descriptor we're using is stdin, and it's actually writing this into the stack, the result, and then branching to that part of the stack as though it's a valid function pointer, which is pretty harrowing and like a glaring example of a code execution vulnerability. But it means that if you're actually reverse engineering this binary, you're not going to know what will happen, just by reading the source code in a straightforward way. So why are we looking at binaries? Why are binaries so important? Well, there's a big schism between source code and actual binary behavior sometimes, and you can see this in terms of how security people have panicked about compiler optimizations over the years. And one of the good examples is something called memsad, which is vulnerability or a kind of a lack of code etiquette that causes optimizations to remove certain secure operations. So in this example, we have a password that's being stored on the stack in the PASSWD variable, And at the end, you obviously don't want to have this lying around in the stack, so you try to clear the variable. You want to mem set it to 0. But unfortunately, under certain compiler optimizations, it will actually just remove this mem set, because the compiler checks that you're referencing a variable you're not going to use, so this operation is useless to me. I don't need to actually run this mem set. It's setting it to 0, and you're not using it. It'll optimize it out, which means that password will stay on the stack. And if you still don't know why this is a problem, you've got to think about problems like stack leaks, things like Heartbleed, things like out of bounds reads. Those kind of things make this very, very dangerous to have lying around, especially for sensitive data like a password. Another glaring example, which I stole from someone's blog, is this idea that when you have two threads working on something at the same time, a typical setup is that you have a context variable. So CTX is the context, and it has a variable n, and in this nested loop, n is going to be used to exit that loop. So when you have this data and you mod it by 2, you check if it's even or odd. Another thread will actually flip n on and off. So it'll make it 1 or 0, and you can control essentially when this while loop will exit. Otherwise, it'll just keep spinning in that while loop. Now, when you compile this into a binary, it turns out that compiler optimizations can drastically change the picture of what's going to happen in that indefinite loop. Because look at the code again, you're referencing this n, and in the compiler will have different optimizations for it, because in this function, n doesn't change. You don't actually change n, something out of context changes it. So what happens is when you compile this under certain optimizations, it drastically changes the picture and will actually introduce an undefined state that can cause a memory a race condition, because it just skips the check of the sentinel entirely and just makes like an indefinite loop. So this will introduce a race condition if you're not entirely sure. So on the one hand, you're checking it faithfully. On the other hand, you optimize so aggressively that it says, oh, you're not going to change this n variable, so it optimizes out completely. So that shows you there's a chasm that can open between binary and source code, and you probably want to check your analysis against an actual literal binary definition before trusting that the source code is secure or not. So just a summary of the hard problems in reverse engineering. You have binary formats that need to be interpreted, and the other kind of key point is derivation of control flow graphs are very hard, because you have data-dependent branching, complex point arithmetic, dynamic loading and resolution, and optimizations that can change the view. So now we know it's hard about reverse engineering, but symbolic execution, this kind of new emerging technology, not really new, but like for analyzing binaries, it's pretty contemporary. We can now approach these problems in sort of a scientific way, chipping out different program exploration methods, chipping out carving out the slow approaches of symbolizing program paths and analyzing things like algebra and constraint solving. But so what is symbolic execution before we can get to how this is going to help reverse engineering? Symbolic execution is basically a marriage of two pieces of technology: constraint solving, which exists in formal proof theory, formal logic. It's a way of automating theorem proving for certain fields of mathematics, and it's a way of verifying circuit behavior for people who engineer hardware. So if you actually, bake your own chips, you write your own Verilog, there's all these tools that exist for checking that your Verilog circuit is not going to have certain states, and the way it guarantees it's not going to take certain states under given input is by relying on constraint solving and symbolic execution as well. And it marries this old constraint solving technology with the big scary new source code analysis we want to do these days, and it kind of sandwiches them together. But essentially the process is it takes the variables, the if statements, the conditionals, and the various states a program can have, and it distills that into stuff that a theorem prover, constraint solver will enjoy working through. And if you don't know what constraint solving is, just a quick crash course. It's just a reference to the Boolean satisfiability problem in computer science, which is basically the problem of given a formula of Boolean variables, ANDs or ORs and XORs and all these kind of Boolean operations, can you work out the vector of bits that will evaluate that to true? And when you talk about SMT solving, the terminology becomes, can you determine a satisfiable solution to this, or determine that it's unsatisfiable? There's also a third option, because this doesn't have a definite approach. There's no approach to this problem that will for any formula be able to say, yes, you can definitely solve it, no, you can't. There's certain forms that will break down and become solvable, and certain forms that won't. And the third option will be, it's I don't know. I don't know if it's satisfiable, unsatisfiable. There's a third answer that can come out, and this basically happens when the SMT solver gives up. It says, I got it. I don't know how long I have to guess, but it's definitely too long, and it stops guessing it. This is directly related to the halting problem. You can reduce one to the other, or dress one up as the other problem, because if you can answer the Boolean satisfiability problem as we see here, you're saying that, like, why not just reduce a program and its variables to this form, thereby solving the halting problem. If you're looking for halting in a program, you can contrive it as a Boolean satisfiability problem, or Boolean satisfiability problem can be dressed up as a halting problem, or what have you. And the basic process of constraint solving is you take all the conditional statements again, as we see in this picture here. You start with a C program, you rewrite those variables in the if statements in a way that's friendly to conversion to constraints, which is here the person is doing single static assignment a form, which means like each variable is only assigned once. You don't have like multiple assignments for the same variable. And once that's there, you can more easily convert it to Boolean constraints. You're going to break this down into symbolic bit vectors. When you have an int, you're not going to just have one variable. You're going to have a variable for each bit in the int, and break it down like that. Not going to get into the mechanics of it too much, but you're converting a program and its conditional statements. Because let's say you have if statement, nested if statements that reach a certain place. What will happen is, if you want to know what's required to reach that place, you'll actually have to latch on to the variables, these conditions of if this and that if statement and this if statement and this. This is why you see these upside down kind of lambda looking a kind of symbols. That's the and symbol. I don't know if my mouse is going to record now, but this is the and symbol, and this is how you can see various if statements get latched on in a program path. We'll talk about a program path in a second. So the basic process is that you're going to take a C program or a program. In our case, it's a binary. It doesn't matter what the source type is. This works for any programming language. It works for IR, intermediate languages. And as we saw, it works for hardware language. If it works for Verilog, then surely it'll work for the higher level languages as well. So you basically have, if you want to describe a symbolic state and build a symbolic state map, you're going to have three things you need to describe. One is the variable store, two, the path condition, and you're going to have to be able to describe the state as unique. You're going to have the state ID. You don't want to confuse states with one another, so you'll have to be able to uniquely identify them. And the way this works is, as you encounter statements, you symbolize the variables involved, and you record the path statements required to reach those statements. So our first state is representing the path that's required, the stuff that will, it represents the way that the variable store will be affected, and the path condition that needs to be satisfied to reach statement 1 to 3. That statement, program statement 1 to 3, that's symbolic state number I, number 1. And you can see in the variable store, all we've done is symbolize x and y. We said x has to be symbolized as A and y has to be symbolized as B. And the path condition is just simply a true, because nothing needs to happen to actually reach it. You'll always reach it no matter what. So it's just a true. And then at the bottom, just for documentation's sake, we're showing the program state associated to this. Now, when you encounter an if statement, this is very important, you can actually envelop both sides of the if statement in analysis. You can immediately have a view of both sides of this if statement when you want to make decisions. So imagine fuzzing using this. Like, you're not going to have the fuzzer blindly guess, like, oh, just guess until you get both sides. The fuzzer can actually have view of, if I want to reach the one side, I'm gonna look at state number 2, the successor state, and I'm going to say, okay, my path variable requires symbolized variable A plus symbolized variable B to be bigger than 10, and it's going to mean that my variable store will update in this way. Once I've reached it, it'll update A as B minus 1. And so the other side is just a not condition of that. It just says P has to be, A plus B has to be smaller or equal to 10. Okay, that's the not condition of the other side. So now we immediately in Vue have both sides, and we can decide whether they're interesting. Like you can say, is it interesting to our analysis that A should be B minus 10? We don't want to subtract too much from Y. Maybe in our path, we know that for our analysis, we want to look at all the cases where Y is only subtracted from once. So therefore, the only paths we're going to be interested in is the ones where Y it doesn't have the subtraction. You can immediately see that here from just looking at the if statement. So that's kind of the power of this analysis. But this is how we build the path conditions. We update the variable store, and we associate the program statements to it so we can make decisions going forward. So you need to imagine this map, but like involving thousands of different states. And again, states will grow pretty fast. They can grow so fast, in fact, that they overwhelm a analysis, and that's called state explosion. Because as you've just noticed, every time you introduce another state, another if statement, you're gonna fork that state into at least two successes. You could have if then else, or if then if else else. Else if. You could have a bunch of different if statements, which means you explode into even more states. And what they can do is actually make sure that your analysis has so many paths to look at that it just becomes infeasible to look at all of these paths, and that's called state explosion. And obviously the other problem with this is that it's dependent on constraint solving, which means you have to churn through an undefinable amount of time to actually get your answer. So there's just two hard edges to it, which we have to rely on optimization problems to get around. And they're pretty elaborate optimization problems. You can cache constraint solving results. It turns out that normal programs, they don't tend to have wild, introduction of variables. In if statements, they tend to incrementally add conditions. So you would say if A is bigger than C, and then the next time you're not going to do X and Y. Maybe you're going to be if A is bigger than C or bigger than D. You'll kind of latch on to a core form. To core form of constraints. You tend to pick up little adages of constraints, which means you can probably reuse solutions every time you ask a question. It's very useful. It turns out, to do that. Then there's also something called state merging, which means that if you split a state, if statement, and let's look at the previous example again. It's a good example to work from. If you split the successor states, you'll see that in this program they end up reaching the same point. They're both going to reach the same return statement, which means if you don't have any use, let's say there's a longer program beneath this before the return statement. If you don't have any use in maintaining both paths and latching on the same information to both paths, you can just merge them at the end and say, okay, these split at a certain point, but they merge again because both sides will exit the same if statement, essentially. And that's called state merging. It avoids having to maintain two separate paths that will behave exactly the same. And then there's also directed exploration methods, randomized exploration methods, which tell you look, you don't have to explore every single path, go down every single state association or follow every single direction in the state map. You can just stick to the ones that are interesting to your analysis. For instance, you can explore states that will always end in a mem copy, and there's ways to optimize it so you never step down states that don't end up there. That's called directed execution, which I'll show an example of in a second. Now, I talked about state explosion, and this is what it looks like. This is a typical map of some random binaries on an Ubuntu 20.04 machine. And what happens here is I'm graphing execution steps, which is the x-axis, versus active state, which is the y. And I'm showing how fast they grow. So you can look at kind of in relative terms how many steps you'll get before you probably start exploding. So the yellow line, the first yellow line, obviously that's exploded. You're never going to get to 50 steps unless you maybe have a supercomputer, right? It grows pretty fast. And as I said, it's an exponential graph. It's a logarithmic graph. So it looks like a logarithmic graph. So this kind of tells my makes my point pretty succinctly. And so this is another picture of how states grow. This is something I put together with a little tool I wrote, again based on Anger. All it does is step through states. It collects up the symbolic states and works out how they're associated to each other in a directed graph format. So you're looking at one state becomes two states and is reachable from this state to that state. This is actually how this works. It's kind of like a CFG for symbolic states. On the one side we have GNU Debugger, and you can see the actual point where states start exploding and growing at an exponential rate. On the other hand, we have Object Dump, and the interesting thing here is there's definitely loops that you can see, just loosely with your eye in the GNU Debugger picture, and that's obviously because GNU Debugger actually wants to run a program that could happen indefinitely. So you'll definitely have loops that try to iterate the program over and over. And on the other side, you have Object Dump, which isn't going to run anything. It's just going to read a file, and if it doesn't see what it wants, it'll exit. So you're looking at this nice dragon on the one side and a scorpion or something on the other, or what have you. But it's interesting to see the actual behaviors reflected in the symbolic states. It's very, very cool. So what is Anger? Well, basically Anger is a collection of technologies. It comes from some technology that was submitted to the Cyber Grand Challenge that DARPA hosted in 2016, and basically it came together as a bunch of stuff that was meant to help automate vulnerability discovery in binary programs. And the technology that is involved is, first of all, the Capstone disassembly library. So when you throw a binary in, Capstone is going to be doing the heavy lifting in terms of disassembling and making sense of actual executable format. It also relies on something that the Anger team wrote. The Anger team's from UC Santa Barbara. The other thing that they contributed, in-house to this is CLI, the actual binary loader, which stands for CLI loads everything. If you have a Unix beard, you kind of know about these cool recursive acronyms. CLI is trying to evoke memory of those. And the IR language, if you know anything about compilers, you know that an IR language, or intermediate representation language, is going to be part of this whole process, and the one that this is based on is called VexIR. So it's VexIR comes from Valgrind, the Halgrind technologies. It's stuff that used to, I believe, Threat Sanitizer used to be based on this stuff, and then they moved to LLVM, if I'm not mistaken. But VexIR is integrated into a lot of different projects because it just works well, or used to be. And if you want synergy with those things, you want to implement the solutions that they implement for program analysis, you can immediately do that in Anger now because of the way that they supported this stuff. And to turn VexIR into something that a constraint solver likes, it relies on something called Clarify, which takes types and spits them out into, like if you have an integer and you want the integer to be symbolized, it'll spit it out into Z3 in a way that it likes, so you can actually solve constraints based on that. And Anger is the thing that kind of mediates this whole process, models memory, associates stack and block count, depth, and all these nice things to the actual constraint solving you're doing. And obviously, if you want to actually host a session in Anger and symbiotically execute a binary, you're going to need to know about three key things. The first one is the project, the Anger project, the simulation manager, and the sim state. What happens is you load your binary up into a project, you set up a simulation manager, and you step through simulation. The simulation. I'll show you how that looks in a second. And out of that step will come Anger states, sim states. And the sim states allow you to evoke the solver. So once you have a sim state, you can say, hey, solver, from the sim state, what do I need in terms of my symbolic variables to reach this sim state? And you can also look at what the registers will look like, what the memory will look like in that state. You can even add your own plugins to this process as well. As I mentioned, I haven't mentioned this yet, but the simulation manager has stashes. So the stashes will have active, dead-ended, deprioritized states. There's a couple of categories. You can even add your own stashes arbitrarily if you want. It's just an associative dictionary, but the default ones that you need to know about are the active, dead-ended, unsatisfiable and unsatisfiable states. Those are, I think, the ones you're going to be worried about the most. The active states are the ones that can still be stepped forward in execution. The dead-ended ones are the ones that aren't, and the unsatisfiable states are the ones whose constraints are not satisfiable. And there's also like unconstrained states, states that I believe rely on symbolized input. But you can also stuff into the simulation manager exploration techniques of your own, which there's some nice built-in exploration techniques already, things that help you save memory, that keep the program going. There's things that actually direct execution towards certain program states, and I'll show you how they look in a second. But that's basically the spiel. So the workflow is pretty simple. You're going to load a binary into Anger, and this is what the Python looks like for that. Very simple, anger.project, give me a binary. And at this point, I'm not going to show this now, but you can derive a CFG. You can check out the sections and the symbols, and expect actually the alpha properties of the binary, and ask questions around that. The second thing is, like, once you have your binary loaded, you want to build an initial state, and as you can see here, your initial state, you just go project.factory, give me an entry state, and you can actually ask for a full state where everything is symbolized, a blank state where basically nothing is, and a custom state, which is whatever you want to symbolize. Here's a custom state I'm kind of building, where I'm saying, look, I want argv, I want to symbolize argv, the array, and I want 8 position. I want arg count amount of argv arguments, and they got to be 8 bits times whatever length I give it, and I'm also naming them arg something, arg1, arg2, arg3, whatever. And then you just stick that in the entry state, and Bob's your uncle. The other thing that I'm mentioning as optional here is you can actually hook symbols. So you can tell it, hey project, whenever you're in execution and you reach, let's say, pthread create, please call this function. And once you call that function, it's called a sim procedure. You can actually call another function if you like, do a bunch of stuff with the arguments, return from whatever call you made, then continue executing. It's basically like hosting a breakpoint in a debugging session, if you like. So you build a state, you model your variables. Kind of this is already shown in the previous slide, but modeling variables means modeling files, registers, memory, environments, and what have you. And once you have your binary loaded, your environment modeled, you can just step through the simulation manager. And this is straightforward how you do this. You go anger.simulationmanager.step, and you tell it, hey, the stash I want to step is this stash. It doesn't have to be the active stash. It can be the unconstrained states. It can be the unsatisfiable states. But for argument's sake, you probably, by default, you'll be stepping through the active states. And let's look at a quick example. Now, the typical thing that you do when you get a binary is you maybe want to check the static strings. That typically tends to get you some metadata on what to expect. It'll tell you, like, oh, it's going to print this string somewhere, and it's going to do something with that string somewhere else. So it gives you some semantic information, not much. There's not much context to it. But here's an example where that wins you nothing. If you look at this binary, it's checking argv against the string called kmsec, and anyone can tell you, if they can read C, that it basically wants argv1 to be the string kmsec. But if I strings this, I will not see the string kmsec. I'll not see that at all. But when I run this in a tool that I wrote based on Anger, it very easily works out, to get to that string copy. And again, this is the directed execution I was talking about. The tool that I wrote here called Spore Crawler will actually go through the binary and work out how to get to memory sensitive calls. So it'll look for, how do I get to mem copies? How do I get to mem sets, string copies, string n copies? How do I get to functions from a known execution state, which is like just the first executable state? How do I get from that to these dangerous functions? And what does my actual input need to be? So if you read code for vulnerabilities, this is extremely helpful, because it means you don't have to go and cross-reference in the binary on your own. You could be cross-referencing stuff that will never be reached, and it'll take you ages to work that out because of those difficulties I mentioned earlier on. But here, Anger is automating that process completely. It's telling me immediately, you reach the string copy by giving it this string in the argv variable. And Another CTF example of this, that was a contrived one, but here's a simple CTF example. Just if you're using symbolic execution to solve a CTF, the process is incredibly simple, and I'll show you how this works. First step, you want to disassemble it just to get a picture of it. You don't have to, but you do want to kind of see where are we going to aim our session, and it means you need to at least be able to see where certain stuff happens in the binary. And a quick read of this one will show you, hey, it's going to end up in putting either a bad string it's going to print out either bad or good. We obviously want to get to good, so we might not even know this. We might not even know that which one is the good and bad, because if you look at the actual disassembly, here's the two puts instructions, and we don't know really which one's good. But what we can do, because of the power of symbolic execution, is we can just breakpoint at the string compare, and we can say, hey, the reason we want to breakpoint here is just so that everything that needs to be loaded and referenced is there for us. It's not always true because of lazy loading, but this typically means you got everything in front of you that you need once you breakpoint in context of the actual program run. So just to make things a bit easier, I'm going to breakpoint right there. There might be other debugging tricks you got to get around, but for our sake, we're just going to breakpoint there. And then we're going to say, look, I want to target one of these two puts calls. So I want to ask Anger, hey, how do I reach one of these two puts? So just for argument's sake, I'm going to guess that plus 143 in the listing at address OX417. I'm going to guess that that's a good one. I'm going to tell my symbolic execution tool to search for whatever I need to get there. So this is what you're seeing with SciDB search. So it's this is a GNU debugger plugin that I wrote based on Anger, and it's going to target just that. It's going to go, hey, tell me what input I need, and it actually here you can see it work out that you need to put into stdin, not even one of the args. It worked out that you've got to put into stdin the string, and that's exactly what I do. And you can see here in the sort of chopped out screenshot on the left over here, you can see that it actually worked it out properly over here. Yeah, my mouse is there. So that's incredible. I just told it, go for this. Is this the right answer? And it was like, yes, you solved it. So just reviewing what we just did, it's even, sort of embarrassingly quick to describe what just happened, but that's how powerful it is. You kind of can automatically discover input paths. You can target, you can work out what's required to reach memory sensitive calls, thread calls. If you have specific functions that are unique to your binary, you can hook based on those as well. And you can even, if you don't have program symbols available, you can actually filter through paths based on other metadata. You could say, look, my fuzzer seems to get stuck at this block depth, so I'll let the symbolic execution engine run until it reaches, that block depth plus 1. Or I'll let it run until the EIP is at least calling this library, etc., etc. You have all this metadata that you can rely on to automatically explore the binary. So let's make it pretty powerful. And this ability to ask whether states are reachable is extremely powerful, because you can now do amazing things like automatically generate exploits, which I'll show you. I'll show you a reference to a paper in a second that does literally that. It uses Anger to, there's a tool called Anger ROP that actually takes your binary and works out ROP gadgets with certain properties for you automatically. So forget Mona.py, there was the old classic back in the day. Mona.py works out everyone's ROP gadgets through glue and tape and very archaic methods. But this one actually uses symbolic execution to churn through a constraint folder to work out exactly what you need from your properties, from the properties of the ROP gadget. It's a much more autonomously suited process. And the other cool thing that's cool is, with symbolic execution, once you know the path, you know the actual test case. And you can sometimes do this without running the program at all. You can take binaries that are for obscure environments that you don't actually have the metal to run, and you can learn very elaborate things about them, without the actual environments again. So another cool example of this whole spore crawler tool that I was talking about in the previous slide is just so you get the idea. It shows the associated sim state, and this you can use to work out the actual memory address that's being called, or the block that this thing applies in. It shows you the blocks. Here we have a lot of mem copies in the same block. It shows you the actual arguments as well. And there's a bit of a trick to making sure you actually interpret the arguments properly, because they come in, they might come from the solver as like an unconstrained state, or they might actually have to be worked out through again solver interaction. But you get all this context to where things are referenced. And here's another example of that. These mem copies are referencing strings, and because I run this tool, I immediately know what those strings are being used for. So if I see a file name here, it's not just an empty string in the binary that I have to kind of like hope will be called. I know immediately it's reachable. I know it's referenced in a mem copy, and then I know, well, I want the fuzzer to target this file, right? Like I want the fuzzer to open this file and do all kinds of crazy stuff to it, because I definitely will be hitting like lucrative code. So that's the kind of elaborate power it gives you. And just to close, I'm going to talk about some of the other applications. There's this really cool project called FirmUSB, which someone used, I believe someone used Anger in this case, to search through USB firmware using symbolic execution. And basically what it does is it checks for cases of bad USB. So bad USB was when you have these USB devices that pretend to be multiple different peripherals. So what this program does is it looks at the firmware of the USB and says, hey, you've got all these different descriptors for USB functions. Do you actually use them in reachable code? And if you use contrasting descriptors in reachable executable code, again determined by symbolic execution, then we know you're a piece of malware. Like why would a sane USB tool have all these different descriptors? It doesn't make sense. Obviously, it's down to you what's a sane set of descriptors. The other thing that people have done that's pretty cool is Klee Spectre. This is not based on Anger, it's based on Klee, another symbolic execution engine. But basically they said, hey, symbolic execution can unearth all these different properties of reachable code. So we want to see if there's actually cache implications that make Spectre sort of exploitable for the code. Another cool example is just general cache side channels being available in code. And again, the novel example I like is ARG, which actually uses symbolic execution to generate return-oriented exploit payloads. So it takes a binary, it strips out all the gadgets, and then it uses it combines them under certain analysis, and then solves for which one should come before which one using symbolic execution if you want your program to behave a certain way. So that's very, very cool. So these are my references. Please go look at them if you want a lot more elaborate, discussion on symbolic execution and its applications. I also want to make sure that people know where I stole some of my cool pictures from. And that's it for me. That's my website, that's my blog, and my GitLab. Thanks for listening. I hope everyone had fun.